basically there are these possibilities. H naught itself is two cases, true, or it could be false. All right, H naught itself, the absolute truth, it could be true or false. However, when we do hypothesis testing, we don't know. So we have to make a decision. We have to decide to either reject H naught or we accept H naught. Okay. True and reject. Okay, I prefer the other way around. Doesn't matter. Okay. Then you can think, you realize that there will be a table. So if this is true, this is like a given condition. This is like a given condition. You can imagine that there will be four possibilities, right?
Yeah.
Four? Here, this is alpha. This is your 100 alpha percent. The event, the event that is being described here, reject H naught given H naught is true. It's over here. You can imagine there's another way that you can make a mistake, right? If the H naught itself is false, but you accept H naught.
Yeah.
Okay, now that you know this, you can throw away. You just focus on this guy. Extra. This one is called type 1 error. This one is called type 2. The other cases are true, so it's not very relevant. We focus on this fellow. Okay, just ignore the rest. Yeah, not important.
So
okay, maybe
like
ignore this.
2% is more precise than 5%.
2% just means you're less lower probability. Yeah, I guess so. You can say that. Lower probability. But you must think of it in terms of the z-test already, the p-value versus the alpha, comparing the area. Are you in the critical region or not? Okay, we'll get into that later. But one more thing, second one, the definition of p-value. P-value is the probability of obtaining an inequality or maybe inequalities, if it's a two-tailed test, involving the test statistic, such that which is more extreme than the mu equal happy face. So I gave you a template here with arrow bracket. It's just to fill in the blank, okay? Depending on the question. So let's take a look. What is number one? Number one is actually something that involves the z value, okay? So it's an inequality, inequality that involves the z value. So for example, okay, I don't have a good example here, but if you do the critical region method, you'll be able to obtain inequality on the test statistic, right? Let's say it's x, and x is less than some negative 1.96, for example. Then you have to mention this inequality when you're asked to describe the probability. When you're asked to explain what is the meaning of p-value. Okay, that's for number one. Then why did I say inequalities? It's because sometimes there will be a two-tailed test. And let's say you have a variable t, then t could be less than negative 1.96, or t could be more than positive 1.96. Then you have to write down both of those inequalities. Then the other case, part two, is when it's more extreme. So this depends on the context. Whether your H1, your alternate hypothesis, is it a left tail, right tail, or two-tailed test? So what does more extreme refer to? It means that you are inside the critical region. Does that make sense?
Yeah.
Inside critical region. Okay, if you maybe just to help you visualize this, not sure if it's actually useful, but here you have the bell curve. All right. Then if you want to be inside the critical region, what happens is that, let's say I just look at right tail test, for example, the rest are similar. Let's say you have some critical value positive 1.96, for example, and then on the right side will be your alpha. The area to the right is your alpha, okay, for example. Then what we want, if you're doing p-value test, let's say we have some number, let's say 2 here, 2.1 or something, 2.123. And then we try to calculate the right tail area if we are doing a right tail test. Then we obtain this area here to be some p-value. Okay, the right tail area from this example statistic 2.123 all the way to the right. That area is the p-value. Then how do you describe this? You will say that there is this let's say a random variable x, it is more than 2.123, okay, such that more than or equal, doesn't really matter, more than or equals to 2.123, such that it is more extreme, meaning it is more than this 1.96 value, while staying within the same region. Right tail then stay inside the right. Does it make sense?
Oh, yeah, kind of.
Okay. Kind of all. Okay, yeah. Then that's the more extreme part. Then the mu equals happy face. So in this case, this happy face here is actually referring to your the mean that you have written down in your H naught. H0, H naught. Okay, then that's how you phrase it. Probability of obtaining that inequality, which is more extreme, more than compare it with the corresponding test statistic, or not the corresponding quantile value for the corresponding to the alpha, then the mu equals happy face, the value from the H naught. Okay, I will see in an example later. Huh?
Oh, okay.
Okay, clear. That's what I forgot to mention, definition. Then the rest I haven't really talked about it. But the basic idea here is that whenever you know the sigma square, the population variance, you don't need to use the S square anymore. You don't need to calculate the unbiased estimate. Right? Remember sampling, we teach you last lesson, we go through how to calculate the unbiased estimate for the mean, the mu hat, and the S square. Unbiased estimate of the mean and population variance. So here is the application. In hypothesis testing, you need to determine in your original distribution, is your sigma square known or is it unknown? Two cases. If it is known, then we don't need to calculate S square. If it is unknown, we need to calculate S square. Okay, next, you need to know your population distribution. Once your sigma square is known, what is your population distribution, your X? Does it follow a normal, or did they not tell you anything? They just tell you bottles of some cleanser or whatever that doesn't, without stating the distribution. You have to read the question to find out. So if it is normal, you can just say X follows this normal distribution. They'll probably give you the mean and they gave you the sigma square. Then you can say, let me see. Under H naught, X bar follows a normal distribution. Now, notice that I did not mention approximately by CLT since n is large. Why? Why I never say by CLT? I thought every time got X bar then just CLT.
But the population distribution is normal.
It's already normal, exactly. So you don't need to rely on CLT to make sure the X bar is normal. Okay, so the purpose of CLT is when the population distribution is actually
unknown.
Then you need to use CLT. Can you see the pattern? I hope you can see the pattern.
Yeah.
Okay, then what else? Here, just fill in the blank. Here, notice that I'm using sigma square over n, okay, as my test statistic. Okay, this one. What exactly is a test statistic? Just remember, test statistic is a formula that's really just the same as standardization. Go and minus away the mean, divide by the square root of the variance. It's a formula. All right. Yeah, must remember that formula. And you can substitute in values here, here, and here, and here, and you will be able to obtain an actual number for this test statistic. It will be an actual number. Okay, that's a test statistic. Notice that I use sigma square here, because my sigma square is known. Okay, then the second case, if it's known and population unknown, means the X follows a question mark distribution, then sigma square is known, so I can just continue using sigma square over n. Then my distribution will be the same. However, my test statistic will still be the same thing. However, I need to mention this guy, approximately by CLT, since n is large. Because I don't know the distribution of X, I cannot make an immediate conclusion that X bar also follows normal. I need to use CLT to approximately know it is. The X bar is a normal distribution. Okay, then the third case, if it's now third and fourth case, if the sigma square is unknown, then straight away you see a pattern, you have to use S square this time. S square over n instead of sigma square over n, where S is our unbiased estimate. S square is the unbiased estimate of the sigma square. We already went through how to calculate that last lesson. Then normal or unknown for the population distribution of the original X. In that case, if it's normal, we just need to conclude that the X bar will also be normal. Don't need to mention CLT. If it is unknown, then we have to still conclude it is normal, but that's because of CLT. Okay?
Okay.
And these are 4 cases you need to remember. So case 3 and 4, they are more troublesome. You need to calculate S square first. Yeah. Right. Okay, next. Alpha, I mentioned. Okay, this one, I think it's easier if I just go straight into an example before I explain this. This part, also easier if I go straight to the exam. Oh, one more thing I forgot to mention, quite important. This one, method 1, where you use the test statistic value, right? Compare with the critical value, right? The Z value versus the critical value. You take the inverse norm of the alpha. You need to use this. You must use this. If the mu, n, sigma square, or etc., all the other variables in your test statistic. Okay, there's only 4 things. I should just listen down. I don't put etc. So let's recap what's the test statistic that we are using. Z equals to, let's say that the sigma square is known. Then it will be X bar minus away mu naught. This value is from your H naught. Mu equal mu naught. Remember this number, the mean that you're testing. Minus away mu naught, divide by the square root of the variance. In that case, it is sigma square over n because that's the sample mean, the variance. It's not just sigma square over, it's not sigma square over n square. There's no square on the n. It's just sigma square over n. But remember to take our square root to find the standard deviation. Okay, that's our test statistic. So what we need to do is to be able to in order to get this value of the test statistic, right? We can actually do it manually without using a GC. Before GC was invented, this guy can still be calculated. How? That's only if we can substitute the variables with numbers. X bar, the mu naught, the sigma square, and the n. They have to be actual numbers. Then we can get an actual value for Z. Does that make sense?
Yeah.
They need 4 actual numbers. But here, when one of these 4, I forgot to mention X bar, you if any one of these is not available in your test, is not available as an actual number to substitute in to your test statistic, then we have to use method 1. We cannot calculate our p-value anymore. All right, we need to form an inequality involving these values, one of them, or maybe 2 of them. Then we have to solve a simultaneous equation or something. Then we need to solve for these variables. Okay, later I'll show you an example question. Okay, now this is sorry, I forgot to mention this, quite important. You must use the more difficult version of the hypothesis testing, not involving p-value, but involving method 1. So that's when you really need to understand your graph. Especially when these 4 variables, any one of them is unknown. Not available. By not available, I mean cannot sub in with an actual number. Cannot sub in with an actual number. Right? Where did I get these 4 fellows from? It's from the test statistic. Or mu 0, sorry. Usually mu 0 will be given. It's yeah, these guys are usually given. It's the n and the sigma square that's a problem. Okay, maybe I'll circle these 2. Okay, I'll give you an example later. This one, conclusion, I already mentioned last week. Not last week, I mean last lesson. Just have to remember the story to say. Standard essay, need to remember. Okay, and then this is the shorter version. Yeah. All right, then we can begin. Is it not? Let me see. Right. Oh, I just summarized this in a different way. Population distribution can be known or unknown. Sigma square can be known or unknown. Then there will be those 4 cases. Here is a even shorter version where you can go and read on your own.
Okay.
Okay. Yeah, some happy face. What is it? Sigma square or S square over N? If you find I just try to summarize it in different ways for you. If it's confusing, never mind, just use the list. There's only 4 cases: 1, do, re, mi, or fa. Okay. You can go read on your own. The summary, okay, I'll send you later. Anyways, it's actually from the handwritten solution from the ASRJC prelim paper 2, 2020. Okay, let's take a look at your answer. Important point to take note is you need to know the direction. Here you must think in terms of hypothesis testing. H1 is like a enemy, and H0 is your main character in a story. Then you must think in the objective of the main character. In this case, the main character is who? In this case, the main character is a manufacturer. Manufacturer. Then they claim that their length is something. In this case, 300. So you must think in this context, I believe the manager is not just entirely all about profit maximization. He also wants to make sure that they provide the highest quality length of string in the balls of string. They want to make sure that the length is 300 or can be even greater. Maybe I don't put inequality here. Mu more than 300 is desirable for, let's say, the manager of this factory. Okay, then the enemy, H1, right, will go against the desirable. They will say, you sure or not? Are you sure you actually produce strings that are of such high quality? I don't believe you. So you go the opposite direction, mu less than 300. Does that make sense?
Yeah.
Can, yeah, so go the opposite direction. Sometimes it will be more. It depends. Like, for example, in the barber example, the H0 is the boss of the barber shop, or is it the hairdresser? And it takes a certain amount of time to wait in line. So you must think in the point of view of the manager, the boss of the shop. If it's a shorter waiting time, it will be good. If it's but H0 will always be equal. Maybe it's better if I just go to the example.
So I have to define the mu also, right?
Define the mu. Yes, correct. In this case,
I think I didn't do it for a lot of the questions.
Yeah, but actually, do you need to?
Some of the answer key has, some don't have.
Yeah, because usually, I think you can get away with not defining it. It's kind of obvious. But then, just to be complete, actually you should,
Okay.
It's referring to the actual population mean. All right. Yeah. So yeah, basically I'm trying to say here is that the hair salon, they make a claim of 15, right? So mu equal, the H0 is mu equals to 15. All right. But then the H1, this is when you have to be careful. Is it a left tail test, meaning the inequality is less than, or is it right tail test, or is it two tail test? Cool. In this case, because you must think of the objective of the boss. He wants to be provide the highest quality to the customers. So he would make the claim that his waiting time is 15 minutes. Of course, if it's even less than 15 minutes, that's good for him. So what is desirable for the boss? It's less than or equals to 15 waiting time. But now H1 is the enemy. The Jeremy is the enemy. And he wants to go the opposite direction. He wants to disprove the claim that the hair salon provides quality service. So that means that the hair salon, he's trying to say that it's very bad. So bad means more than 15. Wait very long. You get why it's more than 15?
Yeah.
Can, okay. So knowing the direction, that's quite important. If there's not enough context, right, then you just put not equals. Sorry. Yeah, not equals, which is a two-tailed test. Mu1 equals to, I mean, H1 such that mu is not equals to that population, not exactly population mean, the mean that we are testing. Okay, can. Yeah. All right, if you got it right, I'm not gonna go through too much. I'll just read it first. Yes, okay. One more point to take note of is here, they provided the mean and variance, right? So you don't need to calculate the unbiased estimate, right? You can just use it directly. Directly here and there. Okay. Yeah, use the variance given, not the sample variance. Correct. Yes, you should focus on the population. Here, there's a normal distribution, right? Very good. You did not put down by CLT. Very good. Okay, do not put down by CLT here. It is wrong to say that. Because you already started with normal, you don't need to use CLT to conclude that it's also a normal for the X bar. Okay, good. Okay, it's fine. Very good. Then calculate p-value, then you just compare with the alpha. If it's less than alpha, you reject. Yeah, then sufficient evidence to conclude that the alternative hypothesis is true. Okay. Yes, this one is a two-tailed test. Okay, because there's not enough information. You don't know what's good, what's bad. Okay. Can under H0 X bar follows normal. Also very good. You didn't mention by CLT. Should not mention CLT because here X is already assumed to be normal.
Normal.
Yeah, very good. Okay, then what is part 3 saying? Part 3, no, part 2 first. If the test had been for an increase in the mean at a 5% significant level, what would the result of the test have been? Sorry, they mentioned increase in the mean. Increase means is now testing you on alternate hypothesis being right tail test. So that's exactly what you did here. Good. And what happens is that here you should notice that this value and this value, what's the relationship? Times half, right?
Oh, yeah.
Why is that the case? Because you need to draw the graph and see. So in a two-tailed test, you basically have a curve. Okay, don't draw the vertical axis. This is the mean. This case is x equals to 1.85. Then when we do two-tailed test, right, what we are doing is we are calculating some z value here, some z value there. I call it zc and negative zc. And then we want to calculate the right tail areas. I mean the two tail areas. These two areas. The sum of the area of these two parts gives you your p-value. Okay, maybe I'll just highlight. Purple color is referring to this plus that. Does it make sense?
Yeah.
Okay, then the ZC value is dependent on what? Dependent on what? Let's recall what is the test. It's really just a test statistic. And what is the formula? It's x bar minus away mu naught divided by sigma square over n. So it depends on x naught, mu naught, sigma square, and n. When you change the test to a two-tailed test, does any of these four variables change?
No.
No, exactly. That's why the graph will still be exactly the same, but the ZC will still be the same. I don't know what is ZC. I need to go and calculate it. When you're doing the Z test, right, it's also provided actually. The GC is smart enough to calculate for you the Z test. The ZC value in the Z test. It will be automatically provided. You can go and type in a GC to find out what that value is. But here we're doing right tail test. So all we need to do is to ignore the left tail. Okay. Then you realize that it's just one of the tails, right? And they are by symmetry, they must be equal. So you can just times half to get the new area, new p-value. Can make sense?
Yeah.
Yeah. Maybe I should mention ZC is still the same because x naught mu naught, sigma square, and n didn't change. Okay, it didn't change when we are changing the direction from not equal in the H naught to more than. These four values stay the same. Z test statistics stay the same. Means ZC stay the same. Means your right tail area will be just exactly the same as that right tail from the two-tail test. But since this is two of them, and this is only one of them, you can just times half. By symmetry, these two areas are equal. Does it make sense?
Yeah.
Can, huh? Okay, good. Of course, you could just do the entire procedure again. It's just a bit slower. It's also not that slow.
So in the exam, they will accept like just times half.
Can, yes. That's what the solution did actually.
Ooh, okay.
Yeah. It shows your understanding of the concept actually. Okay, anyways, how about part 3? State giving a reason whether it's necessary for the masses to have a normal distribution. What they're saying is the original x, does it have to be normal? Some mu, some sigma square. Oh, shouldn't have had. Does it have to be a normal? What do you say? No, not necessary. Why? Because the sample size sufficiently large, so by CLT, the x bar will be approximately normal already. Exactly. Correct. We don't need the x itself to be normal. We just need the x bar to be normal. Did I mention? I think I mentioned that last lesson, right? Not.
I think so. I think in one of the questions I accidentally put x, not x bar.
Oh, which question? Please let me know when I get there.
Okay, can. I think
Okay.
I think I wrote it somewhere.
Okay. Here is x bar. Yes, correct. So this question, you must realize that the population mean and variance is not provided. They only provide you the summarized data from the sample. So that means that you have to calculate what? Unbiased estimate of the population mean and variance. So that also means that in part 2, later when you're doing hypothesis testing, since those values are not provided, the actual population mean and population variance are not provided, you will have to use the estimate that you calculated from part 1. Make sense?
Yeah.
I hope that's all you did. Let me see. Yeah, you plus 500, you get the mean. Okay, fine. Then this one should be a minus. Okay. Then here, yeah, x equal and x equals. Wait. Hold on. What did you write here? X? Mu? Oh, no. That's wrong. No.
Oops, I think there's
H naught and H1 hypothesis test. That's the English name of the thing you're doing. This is the null hypothesis. That's the alternate hypothesis. Then you're supposed to put the population mean equals to, in this case, 500. Then what tail test are we doing? Left tail equal two tail or right tail? Left tail test. So that's why we put a less than symbol. And then after that, copy down the same number. Must remember this. Must remember this part. And the equal. Actually, this part here is always standardized. This and this you need to change. Okay. Okay, good. Then here it should be the sigma square error carried forward. Okay. Yeah, sorry. No. You actually corrected yourself. Okay. Before you continue doing the hypothesis test. Okay, that's good. And here should be x bar. Okay, can. Yeah, just take note that this is sigma square. So when you key in the GC, you want the Z test, it requires a sigma. You just take the square root of this numerator. Do not include the 50. Yeah. Okay, you got p-value less than the 5%, therefore rejected at 5% level of significance is sufficient evidence to show that alternative hypothesis is true. Okay, can. Next. This one again is the same thing, but here they were clearer. This question is more less ambiguous. They claim that the average length of yarn is at least 300. So that's the objective of the manager, the H naught. H naught's objective is what? I provide the highest quality yarn. I provide more than or equals to 300 meters. That's my objective. But then the suspicious Jeremy, the enemy, he claims, no, your quality is not good. It is actually less than 300. The alternative hypothesis. Okay. So that's why it should be less than. Does it make sense? Must go against the alternative hypothesis, must go against the objective of the manager. or whoever represents the company represents the yarn. I hope that makes sense. Again, this one, you do not put X over here. It should be a mu. Here's how you write mu, like this. It looks like a M, but it's more like a curvy, well, it actually looks more like a U, sorry. A U, but with an extra leg. This is mu. You should be writing mu, not X. Also, you should not be putting equal sign here, should be colon. You did that. Exactly. And also here, the very front part should always be an equal. It should always be an equal. Please go and memorize this. H, not colon. H1 colon. Population mean. Population mean. Equal sign. Then the rest is fill in the blank. The direction. Why are there two happy faces? It's because it could be, the first happy face is to represent the direction. The second happy face is the same thing as the top one. So maybe I should maybe put a star here and a star here. Okay, these two are the same. This guy in the middle is one of those directions. All right, please go and remember this one, the very beginning, cannot get it wrong. Okay.
Okay.
Okay, moving on. Here your correction is wrong. Please change it. More than equal is wrong, should be equal sign. Hey, let me just double check. I didn't look carefully at your previous working. Did you write it correctly? How come the first time you got it right? Not sure what's going on. This one?
I forget.
Okay, please don't forget.
Okay.
This one is fine. Okay, very good. Yeah. Next. What did they ask? It's the same thing all the time. Then part 3, let's take giving a reason whether it's necessary to assume normal. Oh wait, did we go through this already?
Yeah.
I realized you didn't. Oh, no, we haven't go through finish this part. You didn't answer part 3, is it? This is a different question, I think. But it's a no lah, huh? Okay, maybe it looked very similar, the questions. Then you got confused. No need.
Oh, yeah, I didn't see that part. Yeah, because the sample size is sufficiently large.
Yes. Sufficiently large sample size N. It follows normal distribution. Okay, let me just write it. All right, Ken, good. Ken, oh, do you know how to do the critical region test? Like the method 1. Instead of p-value.
A bit confused. Is it use inverse norm?
Yes, you need to use inverse norm, but let me see. I think I actually can show this. Let me set up. I think you can get the value without inverse norm, but yes, inverse norm definitely works. Let me share screen first.
If I use inverse norm, is with 0, 1, right?
Yes, correct. Usually we would want to standardize it to just 0, 1.
Okay.
Assuming the distribution is, assuming you have already standardized. Let me just share screen first. Share window projector here. Is that showing?
Yeah, okay.
Right. Okay, I need to do the following. Wait, loading. There we go. Okay. Hi, why is it not showing? Shrink it down. Is it better? Not really.
Yeah, not really.
Okay, wait. Wow, this is challenging. Sorry. Give me a moment to share the screen nicely. So I need this guy. Yes, okay, good. Now it looks better. Okay, so we can do some hypothesis testing. Let's just do it. So let's just go use this example lah. Since we already have a concrete example, we can just go to stats, go to test, select Z test number 1, enter. Then go to stats mode. There's data and set by default, it should be on stats mode. Then just change the numbers. How about the mu naught? What is it? In this case, your mu naught. Let me see. Let me see my notes. I don't want to make a mistake. Yeah, your mu naught should follow the mean that you are testing, which in this case happens to be 500. Right. Okay.
Yeah.
And go to the next one. Sigma. In this case, you have to be careful. You look at this part over here. Right. Zoom out a bit. X bar follows normal, and this guy, you should be keying in the square root of the numerator 2.5483. So key in square root 2.5483. Okay, enter. And then X bar in this case will be your sample mean, which we have already computed to be the unbiased version, 499.284. Then your sample size N in this case, let me see the question now. 50 bottles, right? 50 bottles here. So N is 50. Then what test are we doing? We're doing a left tail test. So we select the left tail, less than mu naught. Okay, then we can just go down and then calculate. So what do you see here?
Z is negative 3.17.
So let's draw a graph to represent what's going on. So when we have this X bar following this distribution, what happens is that we got a bell curve. This here is X equals to 499.284. Then you have the x-axis. You don't need to know the exact function and what is it, but basically the
you're
y.
drawing something.
Oh, cannot see. Wait, hold on. Oh, you couldn't see what I was keying in. Oh my goodness.
It's okay. I was keying on my end also, so I thought you wanted me to tell you the answer.
Hey, why is it not showing? Sorry. Let me see. Oh, I see. Can you see the screen? Is it moving?
Yeah.
Okay, let me just go back first to what I was doing. Oh, sorry, I didn't know. Z test. Okay, so basically I went to it here. You know how to get to this page, right?
Yeah.
Okay. Then after that, you just have to go. Oh, let me see if it's showing. Okay. Yeah. Then you just press down, and then you fill in the blanks. Yeah. So this sigma, just take note that it has to be the square root of this 2.5483. Okay. I was zooming in just now. Okay. Like this, the 2.5483, you take the square root of that guy. You don't account for the 50. Do not key in 50 here. So yeah, then after that, you can key in the 49.284, the sample mean, and then 50 sample size, 50 of those bottles. And here we're doing a left tail test. That's why I selected the less than mu naught. Then you press calculate. Go down and press calculate. You get this as your answer. So what does it mean? I translate it to the graph. So our x naught here, it follows this mean and this variance. So that means that your mean here will tell you where's your line of symmetry of your bell curve. Okay, so it's 499.284. Okay, should I show both? Okay. Then the variance is whatever, doesn't matter. So what we want to understand from this is when they tell you z equal negative 3.17, it means that there's a y-axis here. Then there's the negative 3.171. Okay, it's over here. Then this is a left tail test. So what does it mean? it means that we are focusing on left tail area. So let me just draw my move it around a bit. So what I want to focus on is this left tail area here. What does this represent? This entire area here. This area here represents what?
Like it will be rejected if it lies in this area.
No. What is that value? What's the area?
What's the area?
Correct. What is the area? If this total area here is 1, what is this purple color area? It is the what value?
The 7.58.
Yes, correct. 7.58 times 10 power -4. Okay.
Yeah.
It is the p value. Okay. That's why I use purple. Purple color p value. Okay. Probability value. All right.
Okay.
Does it make sense? Okay. Can yeah. So that's your p value. Then if you compare with your alpha in this case, what's the percentage? 5% level of significance. It means that we want to get 5% area on the left tail, and it is obvious that this is way less than 5%, 0.05, right?
Yeah.
0.05. I don't know where would it be. I'll have to do an inverse norm for that. Let's see. Second distribution, I go to inverse norm and then I key in the area. In this case, 0.05. But wait, here, what's my mu? What's my sigma? Okay lah. Since the GC can handle it, I can just key in my mu and my sigma directly. So the mu in this case is 499.284, and then after that, my sigma in this case will be the. Okay, we're looking at this entire distribution here. So what we want is the square root of this entire thing, including the 50. So we take the square root first. Then we key in 2.5483 divided by 50. Only for this inverse norm here, that where we are trying to calculate the corresponding x coordinate, the q, the condyle, such that you have a 5% area, left tail area. Then we have to use the entire fraction. You include the divide by 50. The divide by 50, it must be included here. All right. Can then let's just calculate that pace. Then get 498. Oh, what does that mean? It means that you have x equals 498.9. Hey, hold on, is it correct? Did I get it wrong? 0.91. Okay, and this area here, this entire area here is your alpha. I'll just draw it in gray. Okay, maybe gray on gray, not so nice. Orange. Okay, this entire area here is the orange area is your alpha, 5%. I know it's not drawn to scale, but yeah, it is 5%, 0.05. 0.05. Okay, then you can tell the area is less than this area, so you reject H0. That's what you've been doing so far. But now what I'm trying to bring up is the critical region version of rejecting the H0. So here, what you notice is that there is the critical value after taking inverse norm, 498.91, versus the actual Z test statistic that we calculated, or the GC calculated for us, -3.171. I'll show you later how to calculate it manually, but let's just accept it for now. Then when you see that this guy is less than that guy, meaning that the value of the test statistic is more extreme than the value of the, what do you call this? The critical value, then you'll reject. Does it make sense?
So when I reject, I follow the inverse norm, the value that I get.
From the 5%, you inverse norm, yes, and you get 498.91. Then
because the -3 lies like within the area.
The critical region.
Oh, so you reject. Okay.
Yes, correct.
Okay.
Okay. Yeah, good. Then let me just double check. Yeah. Maybe your presentation wise, you could phrase it like this. You can say from the GC, your Z value just equals to negative 3.171. Then you want to hold on a second. Hey, hold on a second. Oh, I just realized I made a mistake. Right. Right. I made a mistake here. Right. I just realized something. You didn't mention the test statistic in the procedure for all the previous questions. That's no good. Scroll back up to the very first question. Here, missing information. Yes. You need to mention the test statistic.
Oh, what is that? Like the Z equals to the
Z.
X bar minus the.
Yes. In this case, mu naught is this value here, 300.
So I write it right below the hypothesis.
Actually, maybe it shouldn't be here. It should be here, right below. After you mention X bar follows this distribution, then you mention test statistic.
Oh, okay.
I think that would be good. Write it below the X bar follows normal random variable after the CLT, if you're using CLT.
Okay.
So test statistic follows. This one is sigma square over n. Let's just fill in the blank. What is the sigma in this case? 27.4 is your sigma square. Okay. Then divide by n. In this case, how many? 100 balls. Okay, so divide like that. Then you must mention that this follows normal 0, 1 because we are doing standardization here. Can
Can.
Then you must repeat that for all the other questions. I'll leave you to do it yourself. Fill in the blank. Test statistic. Okay, maybe I'll do it for one more. Z equals to X bar minus Y mu naught. In this case, 1506.5. Divide by square root of sigma square over n. What's your sigma in this case? Wait a minute. What did you write here? What is this? Okay. You're writing sigma x square, is it? Wow, cannot, your handwriting.
Yeah, I'm writing that.
No, your x should be a subscript. It looks like a 6x squared to me. This is very confusing. No. You must have one symbol here, then we square that symbol. And the symbol happens to have a subscript of x. Okay, it's like a name tag or something. Let's write it like that. But you don't need to write down, a bit confusing. If you want to write it, you make sure you write it like this, or something similar. And then you just square it. Okay. Let me see first. Sample variance you calculated. All right. Actually, why 19? Let me see. This is hold on a second. This is what question? This is question 2. 109. Should be 109. Oh, this is question 2. 0.109 after you square it. Okay, but anyways, yeah, so that's your S square. So you take the square root of, maybe I write down in general, X bar minus mu naught divided by S square over n. We are using S here because we don't know the sigma square. So you just sub in the S square, which you obtain to be 0.109 divided by n. In this case, what is n? Let me read the question again. There are 11 field bags, so divide by 11. Can?
Can.
Yes, should mention the test statistic. It's a good practice. And then you also mentioned follows normal 0, 1. Why is this useful to mention the test statistic? Because, okay, I'll leave it to you to fill in the rest. Let's just go to that example we are looking at. Which question? Question 4. Sorry, I made a mistake here on the graph. I shouldn't be drawing directly from this X bar. No. I need the test statistic first. Test statistic. After you mention X bar, you mention over here test statistic. Z equals to X bar minus away. In this case, what's the mu naught? Mu naught is the 500 divided by square root of the variance, sigma square over n. In this case, it's 2.5483 over 50. Okay, this guy. Is it clear? This?
Yeah.
Can, huh? Okay, then that is your test statistic, and it follows what distribution? N01. So N01, because we already standardized, minus away mean divide by the square root of variance. So my graph here is totally wrong. I'm so sorry. Please remove that. Let me change it.
Okay.
This, if I just remove my y-axis, I keep my curve. This x 9 of symmetry is not 499.824. No. This graph here is actually for z following N01. So this here is actually x equal to 0. We are drawing the test statistic graph. Okay. Yeah, that makes more sense. I shouldn't be looking at x bar. I should be looking at z. That's why I can calculate a z value here, negative 3.71. Okay. So the procedure we did was the same, but it was for a different graph. It was for the graph, the PDF of the z following N01 distribution. Okay. Then we also calculated the, what was that? Critical value. This guy over here. Actually, I shouldn't have taken the alpha. I shouldn't have taken change the 0 and 1. I should just stick to the same value. Let me see if my GC is showing. Okay, good. So go back to the GC. You should press stat. No, not stat. Second distribution, go to inverse norm, number 3. Then you key in the area 0.05 because here we are calculating, was it left tail area? And then the mu and the sigma don't need to change. Sorry, it should always stay as 0, 1. Okay, then left tail. Yeah, left tail. Select left. Then you press enter. I mean, just paste. And then you get the negative 1.64. That makes more sense. Okay. Negative 1.644. Then from here, the how to present the presentation for the method 1. From the GC, z equals to negative 3.171. And then you say that it is less than or equals to the negative 1.644, which is equals to the critical value. Okay, your z value, negative 3.171, is less than or equal to the critical value. Here you reject H0. Within this region, reject H0. The pink color arrow is honestly not necessary. Okay. Can then from there you can say this implies we reject H0. H0 at the blah 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 whatever you mentioned here. Copy and paste the conclusion. Is that okay?
Okay.
Yes, good. Can moving on. Question 5. Question 5 is fine. Question 6, question mark. You circled the question. Okay, let's take a look. What happened? Let's see. A random sample of 90 batteries used in a particular model of mobile phone is tested. Standby time in hours is measured. Sample mean and sample standard deviation of the standby time are to be this guy and that guy. It's a sample, not the population. So that means we need to calculate the unbiased estimate. Test at the 2% significance level whether the mean standby time is less than 36 hours. Okay, good. So what you need to do, standard procedure. So let's just collect the information here. The mean, the standard deviation. Take note that this is not the population mean, not the population variance. So what do we need to do as a first step? Calculate the unbiased estimate. Did you do that? Yes, you use the formula and then you calculated the unbiased estimate. Sample mean is the same as population mean. Yes, correct. The same formula. So you can just use the same value. Let's just list it down. I can't remember the number. 33.787. So I don't need to keep scrolling back and forth, up and down. So let X something, what's this? What's this letter? H? I don't know. Something lah. Actually, don't need subscript don't need so complicated. So let X, maybe if you want, you should include the units. Oh, this is hours, right? Okay. Try to separate. So like capital X and then small h like that. X hours. X hours denote the standby time of a randomly chosen battery. So the H naught is the mu equals, in this case, what are they testing? They are testing that it's less than 36. So 36 versus H1, which is mu less than 36.0. Yeah, just follow the question. 0.0. All right, then you calculate the X bar in this case. It follows a normal distribution. Bracket, what's the mean? In this case, 33.787, followed by the sigma square, which is not available. Sigma square is not available. So we need to take S square instead. But not just S square, but rather it's S square over
the sample size.
Sample size N. Very good. So let me just write down the formula. X bar follows normal. Mu naught, comma, sigma square, not sigma square, must be S square. Divided by N. Okay, what's missing? Do we know the distribution of X? Is it normal? Did they mention normal distribution?
No.
No, they didn't. So that means that over here, something is missing. What do you need?
The central limit theorem.
Under CLT. Okay. I should mention approximately under CLT. It only converges in distribution as n goes to infinity. But here we're going to assume that n is big, then we just approximate the X bar with a normal distribution, approximately under the central limit theorem, since n equals, what's the size of 90 is large. All right, then using GC, you get p-value bigger than 0.02. It is not rejected. Yes, correct. At a 2% level. It's less than the p-value, then you reject. Because, okay, how do you visualize this? What's going on? What's going on is, mention one more thing. I must mention the Z test. The test statistic, okay. What is it again? Z equals? Tell me. Fraction.
The Z equals to X bar minus the 36 over the 90 over 89.
Square root of?
The
90
S square.
S square. Is it just S square? No, it's S square,
over
N.
the N.
Yes, correct. So this entire fraction. So let me just copy it down. Like this, it follows what distribution?
A normal distribution.
What's the mean and variance?
0, 1.
0, 1, very good. So now we can draw a graph of this test statistics PDF, which will be this fella here. It will have a line of symmetry x equal to 0, the mean 0. Let me draw the x-axis. Then what we have, we know that the p-value is currently what? 0.0419. So is this bigger than 0.5 or less than 0.5?
Less than 0.5.
Less than 0.5. What test are we doing? Left tail test or right tail test?
Left tail.
Left tail test. So that means that we want to have a p-value that will take on this shape. Okay, maybe I draw it here. This vertical line somewhere here, and then some left tail area. Okay, that is your p-value. That's your p-value. Then since straight away I using the GC, actually you can use using your z test, right? You can calculate the z value. But I know for sure that it must be somewhere here, the z. Okay, you know what? To make things more concrete, I think we just calculate the value. Yeah, so let's just calculate that value. Let's go to the GC. Is my GC still showing? Can you see my annotation?
Can.
Okay, go to the GC, press stat, go to test, go to z test, number 1, press enter. Go to stats mode, input INPT input, data and stats, go to stats, go down to fill in the data. So what is the mu naught in this case? It is 36, right?
Yeah.
And what's your sigma? In this case, it will be a sigma will just be replaced with s. So we know s squared is 90 over 89, this fellow, right? Instead of sigma is s now. So s squared is this guy. So we want to find out our s. So you just take the square root of the 90 over 89. So basically this fellow here, but you ignore the denominator 90. Focus on the numerator, then you take the square root. So that's what we're going to do. Second square root 90 over 89. Okay, let me do it this way. 90 multiplied by 12.035. Then you close the bracket and then you divide by, what's the denominator? 89. Then close the bracket. Is this part clear? The square root?
Yeah.
Can don't divide by 90, okay? Enter. And then you get x bar is what? 33.787. Okay. Good. And then what's your sample size? It's 90. Change it. What tail test are we doing? Left tail test. So you select less than mu naught. Okay, then we are finally done. Color doesn't matter. Press calculate. There we go. So negatives z equal negative 6.01801. Blah, blah, blah. So that means that in our graph, we will have this z here is really just negative. Okay, I need more space. Negative. Okay, this value. Definitely, it must be to the left of the line of symmetry. If this z value was 0, what would be the p value here? If your z is 0, then what's the p value? P value in this case, we're doing left tail test, so it's a left tail area. So it will always be from here, then you go all the way to the left. X equals 0 is the line of symmetry. So what's the area here that I highlighted? Mic test, can hear?
Yeah, can.
What's the area?
The 8.8604.
Oh, okay, wait. Oh, sorry. Okay. I think you didn't catch my question, but never mind. Okay, let's follow what you're saying. 8p equals 8.8604 times 10 power negative 10. That is the area of the p value. Can you shade in on this diagram? Where is my 8.8604 times 10 power negative 10? Can you shade for me? Maybe I zoom in. Yeah, okay, correct, yes. Good, so I'll just shade it in pink. Okay, it just keeps going down. Sorry, my graph should be it should go downwards all the way. It shouldn't, it's sort of tilting upwards already. Wrong. It should go downwards all the way. Okay, let me try and make it a bit like so. Yeah, so it goes downwards all the way. Yeah. So and it doesn't exceed the x-axis. Anyways, That pink color area, very, very, very tiny area, is the 8.8604. All right. Now, my question was, if let's say in a alternate universe that we manage to get a z value that happens to be exactly equals to 0. Okay, then what will be, can you shade in for me what will my p value here be? If in an alternate universe and totally different scenario. Can you shade in my p value? The area, which part of the graph are we looking at? If z was actually 0.
Uh,
Left tail area, right? So start from z equals to 0. Where do you shade? Left tail area.
yeah, wait, my annotation suddenly disappeared.
Oh, sorry.
Yeah. Like the whole thing.
Yes, correct. Huh? So basically from here, left tail area all the way. Okay, make sense? That's how you interpret p-value. P-value is always the integral of the function, this mysterious function f of x. It's called the PDF, but it's outside of your syllabus, from negative infinity up to the z value. Does it make sense? This is this?
Yeah.
Or if I bring the formula up, this p area, this is this. The z in this case is negative 6.084. Negative 6.018. Can you understand this one?
Yeah.
Can okay, good. So now what are they? Then we are comparing it with the 0.02. What is 0.02? It's basically telling you the left tail area is 2%, 0.02. So here we got very, very small value. 0.02 means you have another critical value here. Okay, let me just toss this away. Not relevant to the question. You're comparing with what? Let's read the question again. We calculated a p-value, we compare it with the 2% level of significance, and then we concluded to not reject. Why is that the case? Because here, hold on a second, let me think. Right. Oh, okay. Okay, let me just bring this a bit closer. Then we concluded that it's more than 0.02. So what is 0.02? It's actually some area over, let's say I draw a vertical line over here, then there's some z, what I call z critical. Can you see my annotation?
Can.
Everything okay? Okay, good. Then we want to find the 0.02. What is 0.02? It's actually this region here, the green part. Okay, that is 0.02. The alpha, significance level. Then how do we calculate this z critical? It's actually just, if I just go to my GC inverse norm of the 0.1. Second distribution inverse norm. 0.02. 2% is 0.02, right? Yes, right? Can you hear? Do you agree it's 0.02? I didn't key wrongly.
Yeah.
Yes, 2% significance level means 2% area. In this case, left tail test, so left tail area. Then we want, what I want to calculate now is the z critical. What is this value? Corresponding critical value such that we can get a left tail area being 2%. So we key that in the calculator, we press enter, and we obtain negative 2.053. Is that right? That seems a bit off. Wait a minute. We calculated a -6. Here, -2. How come -2 on the left? Doesn't make sense. Wait a minute. Let me just double confirm first. I wasn't really looking at the results carefully. Huh, I got a different value for my P compared to yours. Did I key in wrongly? Did I key in something wrongly? Let me see. There's something wrong here. Oh, right. Right, it's not 33, it's 3. Ah, right. Okay. It should not be 33.387. It should be a 36. This guy, the X bar should be a 36, right? No? Is it? Is it?
I think so.
Let me confirm first. Actually, wait a minute. Be the best of 50.2. Hey, actually, okay, can I just make a correction to some of your workings?
Okay.
All the way at the front. Yeah, there was another mistake. Okay, over here, when you write down the X bar, this fella here, it has to follow your mu naught over here. Okay, not the sample mean. Right? Is that?
Yeah.
Is that okay? Can also this value here, and this value here, these three positions they should be the same. Is that okay?
Yeah.
Not related to the sample mean, the weird number they give you, like for example, over here, over 299.2. Okay, right. I realized I forgot to show you how to calculate the z directly manually. Okay, let's just do it for this example. Okay. Okay, can. Yeah, so let's just do that for question 1. Sorry, I will go back to that question 4 later. Okay. Okay.
Yeah.
I hope you can still see the screen, huh? Okay, good. So let's just do this question again, but this time let's take a look at how we can calculate the how we can reject this yeah, how we can not reject this using the other method, using the critical value method. So here's how we proceed. We list down the test statistic after the X bar. Then we proceed to calculate the test statistic, which will be what? Z will actually be, we can calculate it manually to be X bar minus 300 over square root of whatever. In this case, your X bar will be replaced with something. What do you think is the value of X bar? X bar is a sample mean. This fella here. This guy. So we can substitute in. Then we can get the value of our z. So key this in the calculator for me. What do you get? Can you help me to type this in?
The z test.
No. This fraction here. We try to do it manually to convince you why the z test works. Yeah, I'm trying to convince you that the z test works. What do you get? Negative?
Negative 1.4754.
Huh? Wait. Did I key in wrongly? 299.2 minus 300 divided by square root of 27.4.
Oh, I thought that was 29.4. Negative 1.5283.
Yes, correct. 27. Oh, sorry. That's a 7. Yeah, 1.5283. Okay, Ken. So now let's use the z test now. I'll type it in. So we will get the same answer for the z value. So let's see what's the sample size. In this case, let's take a look first. There's 100 false. Okay, good. Then after that, what do we have? We got sigma. We want to calculate sigma. That will be the square root of the 27.4. Okay, so second square root 27.4. All right, good. Next, we want to key in the x bar. What is x bar in this case? What is x bar? X bar is the weird number, the 299.2.
Yeah.
Okay, then finally the sample size 100. No, sorry, I key in the sample size at the wrong place. Oops. Oh no. Mu naught is not 100. Mu naught is the mu naught value in the H naught 300. The sample size is 100, not 1,000. And we are doing what tail test? Left tail test, so less than. Is it okay, this part?
Yeah, can.
Okay, let's calculate it. So what do we get? We get the negative 1.5283 for the z. Can you see that it's the same? Yeah.
Yeah.
Z, yeah. Okay, so we can actually calculate it manually. But then how do you do the z test? You're supposed to say that this is less than the z critical or the critical value, huh? You can also spell it out that way, which is equals to, you type in inverse norm in the calculator. Second distribution inverse norm. What is the percentage we're doing? The alpha percent? 3%.
3%. Yeah.
So 0.03 and 0.1. And we're doing what tail test? Left tail test. So we select left. Then we paste it. So you get negative 1.88. So this is less than negative 1.8807. In other words, your test statistic value negative 1.5283, is more extreme than your critical value. More extreme than your critical value. In the case of a left tail test, more extreme means less than. You can also realize that this is exactly equivalent to the p-value being less than the alpha. How do you draw it graphically? Here's how you draw it. What you have currently is the bell curve representing the n01 for the z. Okay, line of symmetry is over here, x equal to 0, which is really just the y-axis. The x-axis is here. Then we have what? Negative 1.5283. So here is x equals negative 1.5283. Sorry, I shouldn't put x, I should put z, because that's the convention. Z is your test statistic value. Then your z critical is where? Z critical is somewhere on the right side here. Then we are saying we are doing left tail test. The critical region is this left region. The z value is inside this region. Right? It's inside the inequality z less than negative 1.8807. And as a result, we conclude that this must we do not reject H naught. Is that correct?
But I
Oh,
thought
sorry,
it lies
you're wrong direction. Oh yeah, sorry, I got the inequality direction wrong. Oh my goodness. Wow,
Oh,
very blur today. Sorry. This one is more than. Yeah, okay. Let me swap it around. Oh no. Okay, like this. Sorry, I got the direction wrong. Negative 1.5 is bigger than negative 1.8. So in that case, we end up having the other conclusion. Sorry, the test statistic is outside of the critical region, so it's not as extreme. So that in that case, since it's outside of this critical region, we do not reject. Outside critical region.
okay.
Okay, so do not reject. Outside critical region, this implies we do not reject H naught at the 3% level of significance. And then we conclude that there is sufficient evidence to for the H1 to be true. The manufacturer's claim overstates the value of mu. How do you link it to p-value in this case? P-value in this case is what? 0.06326. Can you shade in for me the p-value in the graph? 0.6263216. Sorry, are you shading in?
Yeah.
The P, correct. Yes. Is it right? Hey, wait. Sorry. Maybe I zoom in a bit. This guy, how did we get this? We calculated it from the alpha. That guy, 1.5283, where did we get it? We get it from z-test, or we do it manually. So what's your p-value again? The 0.06321.
This one.
Yes, correct. Okay, good. Yes. This region here, that is your p-value. Then where's your alpha? The area.
Yeah.
Correct. Good. Yes. So if you manage to get a p-value that's bigger than alpha, you reject H naught. Correct?
Yeah.
No. You do not reject H naught. Okay. P-value more than alpha is do not reject. P-value less than alpha, reject H naught. So let's take a look at this diagram. Using this rule here, p-value is currently bigger than alpha, so we reject or do not reject.
Wait, but the
Is it
negative 1.5 is the one we got from inverse norm.
No. Really? Is it? Did I get it wrong? No, inverse norm is negative 1.8. This guy is inverse norm. You inverse norm the alpha, 0.03.
So that's the critical region.
Critical region is critical region is this orange arrow here. Z less than or equal to negative 1.8807. Yes.
Then what do I call the negative 1.5, like formally the z value?
The critical value here.
Critical value of the sample.
Is there a name for this? It's just the critical value for this particular example, I guess. It's just critical value. It's just critical value.
Okay.
Is there a formal name for it? Not a more formal name for it.
I'm not sure like how to label, because like there's the Z critical and the critical.
Z critical is the critical value. They are interchangeable. Then this will be the value that you get. And that's just the name. This is the name only. There are only two names, Z critical or the critical value, a number. Is equals to this value you obtain from inverse norm.
Then how about the sample one, like this one?
This guy.
Yeah, I just write Z equals to that.
Correct. Yes, you can do that. You can just write down Z equals to that.
Okay.
It's implied. It's a test statistic value. But you don't need the English name. Just write down Z equals this guy, then follow an inequality, followed by Z critical equal to that guy.
Okay.
I think this presentation should be okay already. Then you have to be careful about the rejecting or not rejecting. If you are within the critical region, then you will reject. Yeah, more extreme. More extreme means within critical region. If you're outside the critical region, then you do not reject. Okay, good. So here, okay, I highlight light blue here, light blue here, light blue here. These three fella should be the same, right? So, right?
Yeah.
Then I realized that you consistently made some mistakes in some of them. Okay, here is fine. Is it right? Here is fine. Okay, these three are the same. That's okay. For question 2, then question 3. Let's see. We need 1.85. Okay, here, and then never mind. I'll just write it in. Z test statistic Z is x bar minus mu naught. In this case, mu naught is 1.85, which is my light blue highlight here. Divide by the square root of the variance. In this case, 0.12 square over 60. Follows normal distribution, mean 0, variance 1. Yeah, so we should put this after you mention the x bar. Insert here. Yeah, so okay, this is fine. I think that I saw a mistake one time. Where is it? 500. Okay, I'll just highlight all of them. This one. I remember I saw one just now. Over here. Yes. Here, wrong. Mistake. Shouldn't be a 499.284. It should be 500. Right. The three light blue highlights. That is your mu naught.
Sorry, can you zoom in? It's like very blurry.
Oh, okay. Wait, hold on. Let me just. Never mind. I'll just get rid of the calculator.
Okay. Thank you so much.
Sorry. Yes. This is what question again? This is currently question 4. What I'm saying is that this, and this should be the same values. Okay. Your H naught mu equal 500, followed by your X bar. The mean should also be your that 500 value you're testing. And then when you try to get your test statistic, you subtract away that same 500. The only time that you key in this 499.284 is inside the X bar.
Oh. Okay.
X bar is your 499.284. Over the X bar by X bar, I'm referring to this X bar here. Okay.
Mm.
Yeah. Okay. Is that all? Is that all to this? I think that's fine. Your answer here is okay already. Then yeah, so we get our Z value to be less than or equals to the critical value, Z crit. If you really wanted to call it, you can also call it Z crit. Like this. Right? Just like similar to what I did just now. Then we reject H naught. Yeah. Inside the critical region. Okay, we have been doing a lot of left tail tests. I need to do some right tail tests to show you. But there are almost always left tail tests because that's the context. That's the most common. Over here, another one. What should this be? Instead of 299.4 here?
300.
Should be 300. Okay. And then of course, can you tell me what's the just fill it in? Let's tell me what's the test statistic.
The follows n.
Equals first. Follows
Oh.
n01. But what's in between the fraction?
The X bar minus 300 over the square root of 1204 over 99 over 100.
Okay, good. Take a square root. Yeah, correct. Good. Then from there, okay, let's just since you already wrote it down, let's try to do the method one. How do we make sure we can reject this H naught? Here's how we do it. Draw the graph first. This is normal distribution Zn01's distribution. I mean, sorry, PDF, not distribution, probability density function. But you don't really need to know that. Just need to know it's the bell curve representing it. And the line of symmetry is what? X equals to the mean, the mu, which is 0. Right? Because it's 0, 1. Then 0, 1, so 0 is the mean. Then line of symmetry is 0. How do we calculate the test statistic value, the Z? Then later we need to put an inequality, less than, equal, more than. Then we calculate the critical value.
Use the GC.
Use the GC. Okay, fine. Use the GC. I hope you have the page. I'm gonna change screen now to just and like this. Easier to see. Okay, then we can go to step. We go to test. Okay, you can't see the question now, but I'm just going to read off. So what we know is the mu naught is supposed to be the thing we are testing. The manager's claim 300. Then the sigma is what? Square root of the numerator. Don't include the divide by 100. So it's a square root of the fraction 1204 over 99. Oh no. Sorry, let me try and type it again. Square root of, what is it? 1204 divided by 99. Is that right? Yeah, close the bracket, enter. Then what's my X bar? What is my X bar?
The 299.4.
Very good. Okay, 299.4, the sample mean they provided. And then you press enter. And then what's my 100? What's my N? Is it 100? Yes. Okay. Then what's the tail? Left tail,
left
two tail,
tail.
right tail? Left tail test. Very good. Then you press calculate. Yeah. Press too many times. Oh no. Down. Enter. Okay, good. Yes, that's how we get the negative 1.72. Let me copy this down before I change my screen. And then we also have that p value, which you've already written down. Okay, let me change screen back to my iPad. Hold on a second. Okay, good. So what do I want to say? Yes. So this guy, negative 1.7205, actually we can also calculate it manually by using the formula over here. All we need to do is to substitute the x bar with
the 299.4.
exactly. So this guy is literally that formula there, the test statistic, but you replace x bar with 299.4. Everything else remains. Okay, you know what? I can just copy and paste, right? Then replace the x bar with 299.4. Okay. Let me see. 1204 divided by 99 over 100. And yes, I got the same value. Okay. Can okay, good. Yes. So now we got the, what do you call this? Test statistic value. Yeah, just write Z lah. Good enough. Okay, don't write it. Don't confuse you. Test statistic value. Then you check with the critical value. What's the critical value?
The negative 1.7205.
No. That is your test statistic, which we calculated already. No. What do we need for the critical value? What is critical value?
You need to do inverse norm.
Inverse norm. Inverse norm of, okay. Do I need to show you? I think I better show it, just to be safe. So inverse norm means what? You have to press stat. Not stat. You have to press second distribution, scroll down to the correct number. In this case, for mine, it's 3 inverse norm. Press enter. Then you key in the area. What is the area here?
0.05.
Very good, because it is 5% level of significance, so 0.05. Then mu 0, sigma is 1, square root of 1. Then what's the tail? Left tail, two tail, right tail? Left tail, because of alternate hypothesis. Alternate hypothesis. Yeah, so you get the negative 1.6448. Okay, let me copy this down. Negative 1.6448. And I change my screen back to my iPad. I think this is the best way to go. I can't show both on the same screen. Its quality is too low. Okay. Zoom in. Good. So we get the negative 1.6448, which I've written down over here. Okay, the critical value which we got from inverse norm. Then what do we do? Compare this guy versus that guy. More than, equal, or less than? Which one?
It's less than.
Okay, very good. So then we fill in the blank, we put in a less than symbol, which means that if we just draw it on our graph, where's negative 1.725? Here is my Z value, the test statistic value, negative 1.7205. Where is my critical value?
It lies to the right.
To the right side. So somewhere here, critical value, I'll call it Z crit. Just a funny symbol to represent it. Negative 1.6448. So where is my rejection region or critical region? It's over here from Z crit all the way to the left. Why left? Because it's a left tail test. Then this test statistic value lies inside the critical region. So therefore we
reject.
Exactly. We reject the H0 at 5% level of significance. And we conclude that there is sufficient evidence to say that the H1 is true. Okay, maybe your sentence need to fill in the blank a bit more. And conclude that there is sufficient evidence. Oh no, not enough space. Sufficient evidence that H1 is true. Of course, you try not to just write down H1. Contextualize. What is H1? That the length of yarn in a ball is less than 300. On here, I'm lazy, so I write down H1. But you should say sufficient evidence that the length of yarn in a ball is less than 300. True, don't need to write is true, is or is not. English, you just phrase it in a grammatical way. All right. And also you can compare. This rejecting inside critical region, therefore you reject. is the same as the probability p-value. Your p-value is currently where? Your p-value is currently this part here, right?
Yeah.
Then where is your alpha? 5%. It's here, right? This orange one?
Yeah.
5%, I'll highlight it. P-value 0.427. Since the area is p-value, the area is less than the alpha orange color area. Therefore, we conclude that we reject H. Okay.
Okay.
Okay, good. Moving on. So now, back to question 6. Okay, what was the mistake over here? This is not 33.787 here. It should just be 36. Right?
Yeah.
That's all. Because you need the 3 light blue regions, 36 here, and your test statistic 36 here. Can remember the 3 numbers that are the same?
Yeah.
Okay, good. So now this guy p-value is 0.414. I believe I keyed in wrongly. Let me show you. Is it a good idea to show on both screens? Okay, let me try. I think it's easier if I show both. All right, I need to do this. Oh, okay. Let me go to the right screen first. Am I sharing the correct screen? Oh no. Can see on the shared screen?
Yeah.
Okay, good. Move around. Oh, cannot. Oh, how do I make sure that you can? I cannot click away. All right. Like this. Okay, can. Good. So, let's just carry on. So, what do I want now? I want to calculate the. Okay, I want to verify that your p-value is the 0.419. Okay, so how do we do that? Let's just go to stat, go to test, go to z-test, then you key in the value. So mu naught in this case is, what is it? 36, right?
Yeah.
Okay, good. Then after that, what's your sigma? Sigma will just be square root of the numerator in this fraction on the right side. Yeah, so it's square root of the 90 multiplied by, what's that value? 12.053 square. Okay, 35 bracket power 2, but then you have to divide by 89. Then you close the bracket. Over here, right? 90 over 89 times 12.035 bracket square. Enter, and then what's your x bar?
The Oh, I cannot see. It's very blurry.
Oh, okay.
The 33.787.
Yeah, okay, good. Yes. Let me see why it's so blurry. If I just, is it clearer now?
Yeah. Yeah, it's clearer.
Oh, right. Oh, that's how you do it. Okay. Okay. Yeah. Let's just continue keying in. So x bar is your 33.787, right?
Yeah.
Okay. And then sample size is what? Sample size in this case, I can't remember. There's 90 battery, so 90. So we key in 90. Enter. What's the tail test? Left tail test.
Yeah.
We can calculate it. Hey, let's just try drawing it. What happens if we draw? Oh, what's that? What did they just draw? What they drew for you is the z value here at the corner, if you can see. Right, this x coordinate is our z coordinate is z equal negative 1.7347, and the area, the left tail area is 0.0414. Okay, that's what. So you can have done that with your GCR, but you should be able to visualize this on your own. So let's just go back to the test. C test, go down all the way, then select calculate. This is what we really need. So if you see my screen here, right?
Yeah.
Let me see. If I just whoa, that ain't right. I don't know how to use OBS. This is too difficult. Okay. Let me see. Okay. So what do I want to say? Right, we can draw that graph that we saw on the GC. So we draw the curve, center at 0, and then this is the negative 6.0. Oh, actually, I calculated the value wrongly. This shouldn't be negative 6. It should be what value? It should be negative 1.73. So yeah, negative 1.734. Does it make sense? Then this pink color area here is your probability, which I calculated wrongly just now. It should actually be 0.04139. Sorry for the miscalculation.
Yeah.
Is this clear? The area?
Yeah.
Is this part? Then here we are comparing with 2% level of significance, which is this region on the left. And it happens to be smaller, which means that our p-value is bigger than the alpha. And so we reject. Hey, no, we do not reject. We do not reject. Or you can think of it like the critical region is from Z critical here, negative 2.053 all the way to the left, because it's the left tail area. And our test statistic value is outside of the critical region. Therefore, we do not reject. Okay, inside critical region, p-value is smaller, you reject. Let me write it down in case I confuse you.
Oh, yeah.
If it's the opposite case, more than or more than equal, the equality case doesn't really matter. Then you have to accept H0. Or not reject H0. Sorry, you cannot say accept. You cannot accept. You have to fail to reject. You just failed to find enough evidence to reject it. Yeah. What did I want to say? Right. Okay. Next part of the question. Nothing else to say. That is for the first part. Sorry for taking so long. That when you compare with a 2% level of significance. So now we continue the story. Question 6. This type of battery is advertised as having a talk time of less than 5 hours. In a test at the 5% significance level, you found that there is significant evidence that the population mean talk time is actually less than 5 hours. Oh, so the claim in the advertisement was wrong. Using only this information and giving a reason in each case, state whether each of the following statements is necessarily true, necessarily false, or ambiguous. Not sure. Part A, there is a significant evidence at the 10% significance level that the population mean talk time is less than 5 hours. So what you need to do here is not to go and do some calculation, because we cannot do the calculation. Okay, there is no mean, there's no variance given to us. Right?
Yeah.
Can we use the mean and variance from previous? I don't think so lah. Definitely not lah. Actually, is it true? Let me think of it. Let me see. Do you want to use those values when it's 10% and 5%? Actually, you can but the purpose of this question, right, is for you to not recalculate what is the p value, then you compare with the 10%, p value compare with the 5%. No. The purpose is for you to understand what it means when you change the significance level. You don't need to do any recalculations. So let me just draw some graph for you. Maybe I'll take a screenshot of the question as well. Okay, that was the question. Oh, it's lagging a lot. Okay, so what happened here? What happened here is that we changed our significance level. Previously, it was how many percent? In the first half of the question. What was my alpha? 0.0.
The 0.04.
Huh? Wait. 4? Why 4? No, it's 2.
Oh.
2% now. Right?
Yeah.
Correct. We are so far. Sorry, we are going very slowly. I need to go a bit faster. This one is only 2%, right? Okay, good. Then now we are doing a test where the talk time they tell you is it's a different scenario. So actually, yeah, we cannot really use the information from before. Yeah, talk time is different from the standby time. So this line, you draw a line, it's a totally separate question using separate piece of data. We do not have they did not provide us with the sample mean or standard deviation for this talk time. Previously it was standby time, now we changed to talk time. So it's a totally different question. They tell us that, okay, I copy down the question already. They tell us that talk time is less than 5 hours. 5% significance level, you can find significant evidence to reject it. So what this means is we can construct a hypothesis test, totally separate question. So that's why we construct a separate hypothesis test. H0 is what? That's mu, H0 is mu equals. H1 is what? Mu something. What is it? The original claim is the advertisement is 5 hours, right? So mu equal to 5. Is that okay?
Yeah.
Then we found evidence that is less than 5. So alternative hypothesis is less than 5. Is this okay?
Yeah.
And so they tell us that we reject the H0 at the 5% level of significance. So we can draw a graph. Okay, we know that there will be some X bar that follows normal distribution by CLT, and then if n is large, by CLT, n is large. For some mean, okay, it should be still 5. Then for some sigma square over n. But we don't have all these values, right? We don't have all these values. But what we do know is that we have to do what? We have to, in a test at the 5% significance level, we found that there is significant evidence that the mean time is less than 5 hours, which means what? Do we reject H0 or do we do not reject H0? It's less. So reject H0 or do not reject H0?
It is less than the Z critical.
No. Read just this sentence from the question. Is it too small? There is significant evidence that the population mean talk time is less than 5 hours. Mu represents the mean talk time in hours.
So reject the H0.
Very good, exactly. So this part here, if you translate the English, it just means in our mathematical terms, we reject H0. How do we reject H0 again? In terms of the second method, the p-value method. This is exactly the same as equivalent to?
Yeah.
P-value being what? Compare with the significance. Significance level 5%, or in other words, 0. I don't slash 0.05. In other words, what's the inequality here? when we want to reject H naught, the P value versus the 5% alpha, 100 alpha percent.
It must be less than 0.05.
Very good. P value is really just area under a curve, right? So in the solution, if you looked at it, it's they let this be, let this P value be P1. Also, they denote it by P1. So from here, because of the conclusion, we can conclude that the P value is less than 0.05, even without knowing the unbiased estimate of the sample variance or the actual population variance. Even without knowing that, neither do we know the sample size. We are still able to make some conclusion about the graph. Here is how the graph will look. Okay, how about you tell me some of the information. I draw the graph first. So this line of symmetry, what is it equal to? X equals?
5.
No. Oh, sorry, I forgot to mention one more thing. Wrong. We need to, from here, conclude that there's a test statistic. Z equals to the X bar. In this case, we don't know what is X bar because they never provided it to us. Minus away mu naught. Okay, this one they provided a 5. Divide by the square root of question mark square over upside down question mark. It follows N01. Okay, guaranteed, N01. So the graph we are drawing here is not this guy. Sorry if I confused you at the beginning. We follow this guy instead. Oh, so this is the graph for the bell curve for ZN01. Then can you tell me what's the line of symmetry this like?
0.
Very good, it's 0. Okay, so what else? We know that P value is less than 0.05. So how would the graph look? How do you get the 0.05?
From the
label
significance level.
Yes, correct. 5%. You have to take inverse. Okay, you find inverse norm is to find the whatever critical value. But do you want to know the critical value? It's not very important.
Oh, then don't need.
Avoid it. Then there's also the test statistic, the Z itself. Now we want to reject, right? Means P value less than 0.05. So it can only mean that the Z value is also less than the Z crit. Correct? Left tail test?
Yeah.
Inside the critical region. So that's means less than Z crit, then we reject. So P value is where? Let's just color it in purple. This would be the area here, right?
Yeah.
Then where's my 0.05? Let's use orange color. So it must be this part here, right?
Yeah.
Okay, good. So now what happens in my test statistic here? There's a 5 that, okay, there are 4 variables involved here. The X bar, the 5, sigma square, and then N. Okay, or it could be S square over N. Now these values if you continue reading the question, what happens? Did they change? Did they say that they will change the sample mean? Did they say that they will change the sample size? Move to part A.
No.
No, so it means it stays the same, which means our graph also stays the same. Okay, then now part A is saying, which also means what? Which also means our P value will stay the same, right?
Yeah.
So this purple color is a fixed constant. Oh, that's denoted by P1. If you want P1, whatever, just the purple area. Then part A is asking us now. Now we change the alpha to 100 alpha percent to 10%. And we do the same thing again for the hypothesis test. Check whether talk time is less than 5 hours. So what changes? This is not exactly puppy. This is like a second part. Yeah, what changes? What changes in your graph? All this is given information. Now we are finally starting our part B.
The mean.
Mean got changed, right? They didn't mention the mean at all. They didn't review the mean. Or the 5, are you talking about 5? No, still 5. Or were you talking about like X bar? They didn't give us X bar. They also never mentioned it's changed. So we can assume it stays the same. So, but what's the only thing that changed?
They say the population mean talk time is less than 5 hours.
Yes, correct. Which is the same as what they mentioned at the beginning here. So was there any change about what they are testing? This is what they are trying to test. Did they change anything? At least for this less than 5 hours part, there is no change, right? It's exactly the same.
Yeah.
What's the only thing that is different here? Significant evidence at 10%. And this translates to the orange color area, right? So that means we change the 0.05 to 0.10. So graphically, how would it look? Let's draw the same graph again, but this time, what happened? What changes?
The significance level.
So, oh my goodness, everything is being blocked. Okay, let me just bring it down to the side. Like this. Yeah, so the only thing that is changed here is maybe I should just make the screen bigger. I cannot use the GC here. Right? They didn't provide enough information for us to use the GC. We have to really draw a graph and understand what's going on. Here, the orange color area will change. What we need now is to change our Z critical into something else. Let me just get rid of the orange area first. What we need now is a p-value that is still the same. You draw a question mark and then compare it with 0.10. Now 0.10, maybe I use a different color. I use light blue, okay? So it must be something like this, right?
Yeah.
Can you see the 0.10? Now, question, is 0.10 bigger than or smaller than 0.05?
Bigger.
Bigger, right? So where's my orange area actually? It's somewhere in the middle. Can you see?
Yeah.
I'm drawing a lot of things. Purple area is our p-value. Orange is our original significance 5% area. And then light blue is our new significance level. So previously you already so in order for you to okay, no, sorry. Let's just look at the graph directly. Can you tell me p-value, the purple one versus the blue one? What's the direction? P-value is the purple area. 0.10 is the light blue area. What's the direction?
Less than 0.10.
Exactly, right? That's because at the beginning, it was already less than 0.05. And of course, 0.05 is less than 0.10. Purple is less than orange. And obviously, orange is less than blue. So therefore, purple is less than blue. Does it make sense?
Yeah.
Okay, good. So what does this mean? P-value is less than our current new significance level.
So it is rejected.
Exactly. So therefore, you reject H. So we can answer the question already. Part 1, is it necessarily true, necessarily false, or unknown, ambiguous? Using only this information and giving a reason in each case, state whether each of the following statements is true or false. Here, part A is saying there is significant evidence that the population mean talk time is less than 5 hours. What does that actually mean? It actually means this is the second half of the conclusion when you're rejecting H0, right?
Yeah.
This is like saying that sufficient evidence that the H1 is true. So that just means you are rejecting H0. And in this case, we have managed to prove that the p-value must be less than the new significance level, which implies that you have to reject H0. So that means this is exactly the same as, sorry, I should complete the sentence, reject H0 and conclude that there is sufficient evidence to accept H1. Okay, conclude that there is sufficient evidence to accept H1. Oh, so that means that this answer must be necessarily true. Confirm must be true. Is that okay?
Yeah.
Just draw the graph and present it this way. Honestly, this part is what you need. Maybe you can even label it like this. This is 0.05. Now highlight it in orange, just to be clear. This part is 0.10. Okay, can?
Yeah.
P-value less than the significance level, then you can reject. Now let's move on to the next part B. There is significant evidence. The next claim, you want to determine whether this is confirmed true, confirmed false, or don't know. Part 1, part 2, part 3. Part B says there is significant evidence at the 5% significance level that the population mean talk time is not 5 hours. What does not 5 hours refer to? Compare it with less than.
Like it's
What tail test?
two-tail.
Two-tail test, exactly. You need to do a two-tail test. And here they say there is significant evidence. So can you tell me what's your H0 and what's your H1 that we're doing here? Mu equals to 5.
Equals
Then
to 5. Then
mu
it's not equal to 5.
equal to 5. Then there is significant evidence. That's the second half of our conclusion where we reject or don't reject H0.
So the H0 is rejected.
Correct. So let's just write it down to remind ourselves, reject H0. We want to check whether we can reject H0. We want to check whether we can or cannot reject H0 at the 5% significance level when we are doing two-tail tests. Now, when we are doing two-tail tests, something changes. What happens? Your area will change. Okay? Let me just copy this two-tail test. In part B, two-tail test, right? It means we will still again have the same procedure of finding some sort of X bar, following a normal, mean is 5, then the variance is question mark by CLT, assuming n is approximately by CLT, given n is large. Since we're going to assume n is large, more than 30. Or equal. Or equal. Then from there, we can construct another test statistic. If we were given the values for the variance and all that, then of course we can do the calculation. We can use GC to calculate test statistic and all that. Oh, here I put S squared over N. I don't know if they never give us anything. So we can't really conclude whether it's sigma squared or S squared. So everything just can fill in with a variable, but we can't do anything because we don't know those numbers. But what we do know is that it will follow a normal distribution, 0, 1. Which means that we can then construct a graph. But this time, what tail test are we doing?
Two-tail.
Two-tail test. Okay, let's just tell me again what's the equation of this line again?
0.
0. Two-tail test means we have to cut here and there, and it has to be symmetrical. Area on the left and on the right is the same, right?
Yeah.
Okay. Now, what is the requirement for us to reject H0 at 5% significance level?
The p-value must be less than 0.05.
Yes, correct. But here it's a two-tail test, so something special happens. Something special happens. Your p-value is what? Let's say that we manage to find a certain, let me draw a nicer graph. We managed to get some Z test statistic. Like we sub in X0, sub in this one, sub in S, sub in N, calculate this value, we get an actual test statistic here. And then we will also have another equivalent negative Z. Now, right. Then what do I want to say? Let's say we get those test statistics already. The p-value is actually the sum of these two left tail areas, right?
Yeah.
So what happens in your original, from the original P1, right? Remember the P1? What happens to your original P1 in a two-tail test?
It like times half.
The sum of these two must still add up to, the sum must still be P1. But then that means that each piece must now be what? Must be P1 divided by 2, P1 divided by 2. Agree?
Yeah.
Okay, good. Then how about your significance level? We'll also do the same thing, right? You have to divide by 2. Okay, maybe this is a bit confusing. I'll just put a half in front. All right, it will have to also be halved. In this case, what is our significance level? In part B, let's read the question. They mentioned they want 5% significance level, correct? 5% significance level. So that means our area here will also have to be split into half. Does it make sense?
The significance level?
Yes, correct. The significance level. Previously, what we got like a orange area left tail, then blue color area. The 5% and 10%, right? Now my question is, in a two-tail test, what happens to your 5% and your 10%? It will also, my answer to that is it will also split in half. So we need the sum of 2 critical regions to add up to whatever is the significance level. In this case, the question is talking about 5% significance level. So it means we have to split into half. So 2.5%, 2.5%. It means we need an area. Let's say I split that up into 2 halves, 2.5%, 2.5%. I use brown color. So it means we need 2.5 here and 2.5 there. Can you see the 2 areas? 2.5, yeah. 2.5. So what is the requirement for us to reject H naught? Remember, we want to make sure we reject H naught. So if this is necessarily true, okay, let's just say we want to reject H naught. What do we need? We need our p-value to be more extreme than the significance level. More extreme means what? You are smaller area, right? Can you see that purple is less than the brown? Can you see that purple is less than the brown?
Yeah.
If that is the case, then we can get to reject H naught. Is that okay? Maybe I can. So this would be what the picture that we need in order to reject H naught. The picture we need to reject H naught. Can this picture be true?
True.
How? Let's see. You need half a P1 to be less than 2.5%, which is 0.025, right?
Yeah.
This is, okay, I need more space. How do I get more space? Oh no, let me think. Wait, let me try to make it look. Sorry, give me a moment to draw this. .5% and another copy of 2.5% there, and draw an arrow like this. Okay, yeah. So what we need in order to reject H naught. Sorry. Is that right? Yeah. To reject H naught, we need half P1 to be less than 0.025. Can you agree with this inequality?
Yeah.
And now we also need the half P. Okay. Actually, we also need this other condition to be true, but it happens to be exactly the same because of symmetry. Half P1 is less than 2.5%. So we don't need the n. Sorry. Just this will do. Then if I times 2 to both sides, what do I get? I get P1 to be less than 5%.
Yeah.
Is that okay? Which is really just what you memorize all the way. P value less than the significance level, you will get to reject H naught. Can this be true?
Yes.
Yes, because P1 is the purple. 0.05 is your orange. Is this true?
Yeah.
Yes. So therefore, I think this one is also necessarily true, is it not? Did I get it wrong? I think the answer is not necessarily true, not false. Wait. Hold on. Let me think a bit. Less than 10%. Wait. Hold on. Wait. Hold on. Let me think a bit. Um, 5% level of significance. If we divide by 2, what are they doing here in the solution? They concluded that P2, which is 2P1. Okay, let me share the solution first. This guy, part 2, what did they do? They say H0 is mu equal to 5, H1 is mu not equal to 5, P2 is 2 times of P1. Yes, correct. Two-tailed test, the areas must be, wait, 2P1. Why should it be the case? Oh, right. Correct. The Z critic is the same. So there are 2 copies of it. I got the factor wrong. It's not a half, it's 2. Sorry. Can I try again?
Oh, okay.
Okay. Can. Let me go and draw this again. Okay, I am sorry. Let me redraw this. This is not 2.5%. No. Okay, we need to start with the graph from before. Then we conclude that this guy here is your Z, right? Here. This guy is your Z. Does the Z value change?
No.
It doesn't change. But now we are doing a two-tailed test. So that means that the same Z will get reflected. So we get another Z here. Let's just call it Z prime. If this is this will be negative, then that will be positive. Then if I just erase all that, okay, no, I don't need to erase the other highlighting. Actually, that will be useful to keep the highlighting. The purple area here, does it change? If the Z doesn't change?
No.
No, it doesn't change. It doesn't change. Okay, so that means that by symmetry, because of the two-tailed test, that means the right tail will also have that same area. And we know that if we add them together, this will give us our P value, right? Let's say that we manage to do some calculation and then we eventually get our P value. Let's denote it as, let the P value be equal to P2. Is that okay? P2?
Yeah.
So that means that this area here was previously what? P1, right? But that means by symmetry, the other side will also be P1. Then we can conclude that P2 is actually equals to P1 plus P1, right?
Yeah.
Which is 2P1. Is that okay?
Yeah.
Okay, good. Then since this is 2P1, then we can do some calculation. What do we need? We need at a 5% significance level that we reject H0. Which means that we need this guy to be... Oh, let me think a bit. Getting quite confused. Why did they put 10%? It should be 5%.
I think some of the answer key are a bit weird because got one question they say test at 2%, then they test at 1%.
Oh, is it?
I think it's the other questions.
Other questions, is it? Okay.
Maybe they changed the question, then they never changed the answer or something.
Yes, you're right. Okay, let me think about this. I will get back to you on this one. Okay, I'm gonna make a separate video for this one. Let me think about this. Part B. I will get back to you. Okay. Can Sorry.
Can.
I will move on to other questions. Okay, let me think about this. Why did they put a 10%? Okay. Question 7. Let's see. From the claims received by the company over a long period of time, a random sample of 120 is taken. The values of the claims are summarized by the following: this guy and that guy. Find correct to 2 decimal place the unbiased estimate of the population mean and variance. Okay, you got that. Then what do you understand by the term unbiased estimate? It's an estimate of an unknown population parameter theta, where the expected value of the estimator equals theta. Okay, now technically, unbiased, the definition of bias, right? You haven't really, it's not really in the syllabus. But here is what is going on. Whenever you have a population, or like let's say the population of Singapore, you want to figure out what's the I don't know, the mean salary of the entire nation. X bar, or salary of the entire population. That's too difficult to find because we need every single living human being in the world, ask them what is their salary in our country, then divide by the number of people. Maybe for Singapore, it's small enough, we can do that, but that's very impractical and very expensive. So what we need to do is to take a subset known as the sample. We just take a sample, right, of the population, and then we will have a few people inside. Let's say that there's like, I don't know, 700 people. Sorry? Is it okay?
Yeah.
700 people, n equals 700. So in that case, right, what do we do with this sample? We need to calculate the mean, right? We need to calculate its mean. But in this case, this is what we call a sample mean, okay? Sample mean is different from population mean because population requires the entire nation of Singapore. But sample here only has some of the people. So sample mean here will just be, you take the sum of all of them, then divide by number of people in that population. In this case, like 700. So I equals to 1 to 700. Then this guy, a formula that we come up with so that we can calculate the sample mean, then we can actually substitute in the values. Let's say this guy is, let's say there's 700 data and each of them has a different number. We can add them all together and divide by 700. That's something very concrete and very precise that we can actually maybe even use a computer to help us to calculate that. Then this formula here is what we call a test statistic. Okay, now that you understand, you can roughly understand this idea of test statistic, right? You can, now I can bring up the idea of bias. Now, a test statistic is usually denoted by, let's say, a test statistic is an approximation of the actual population quantity that we're interested in, the population mean in this case. In general, we like to denote it by theta here, and then test statistic, we denote it by a theta hat. Okay, then the definition of bias is a bias of a theta hat, where theta hat is a test statistic, is equals to expectation of let me think. Expectation of theta hat minus away theta. Okay, this is not in your syllabus, but what will happen is that you can now take the expectation of the first guy minus away expectation of the second guy, right? Round bracket, square bracket, doesn't matter. Then if they happen such that this guy is theta, this guy is also theta, then they subtract each other and you get a 0. When it is equals to 0, we call this an unbiased estimator.
Oh.
It's not in your syllabus. But basically, you come up with some magic formula, test statistic, and then you take the expectation of it. Okay, and then you take the bias of it, and you realize it is equals to 0. Then therefore it is unbiased. Does it make sense?
Oh.
Alternatively,
kind of.
They told you expected value equals to theta. They are basically translating this part of the equation into a math expression. So what it means is, what we eventually obtain is this guy, right? You split it up. You wish that it's equal to 0. That's the definition of unbiased. But means bias equal to 0. But if you bring this over to the other side, what do you get? You end up with expectation of theta hat. Okay, sorry for writing my equation upwards. I should be writing downwards, but I'm moving upwards. Expectation of theta hat is equal to expectation of theta. That is what they meant by, and actually this theta is a constant, so you can just simplify as a theta. So that's what they mean. They are basically translating this equation into English. The expected value of the estimator, this guy here, expected value of the theta hat equals to theta.
Mm.
All right. Honestly, do you need to know this? Not really lah. But main takeaway you need from this is that whenever you have the s square, remember there's a n over n minus 1 times the sigma square.
Yeah.
This guy is because of the formula here. In order to satisfy this formula, you need the extra factor. That's all. That's really all you need to know. To ensure that you can satisfy this formula, you need the extra factor. That's the main application of the idea of unbiased. Make sure you have the extra factor. Basically, follow the MF26 closely. This n over n minus 1 is not for fun. The minus 1 is needed. But as to exactly what is this expectation and this bias formula, it's not really in your syllabus. I only learned this in university.
Oh.
Yeah, don't need. No. Go away. Okay, not needed for H2. Why did they ask this? Just know the expected value is the same as the actual population parameter. Yeah, okay, Ken. How about part 3? Population mean denoted by mu dollars using sample data significance test of null hypothesis mu equal 1,000 given alternative hypothesis mu not equals to 1,000 is carried out at the alpha % level of significance. Find a set of values of alpha for which the null hypothesis will be rejected. Okay, good, interesting question, because now we are not allowed to calculate the p-value anymore. Why? Because mu not given. Alpha also not given. How to calculate the p-value? Cannot, right? You cannot use GC. This one requires you to do it manually using the the method one, using the critical region, calculating test statistic, critical value, and comparing. Within the critical region, you reject H0, kind of thing. Okay, let's see what you did. Okay, so you start off with mu equal to 1,000, mu not equal to 1,000, H1, H0, H1. Under H0, you get X bar to be, this guy here shouldn't be the sample, it should just be 1,000. Comma, whoa, hold on a second. Again, sigma square over, sorry, S square, right? Because we have to calculate, we don't have the actual value. Oh, we have the unbiased estimate though, so we can use it, right? Square, then divide by the sample size 120. This is approximately by CLT, as the n is large. Okay, using the z-test, we can calculate p-value. Oh, right. Oh, sorry. This question is not that difficult. Okay. Fine, we can calculate p-value. In order for you to reject this, you need the p-value to be less than the alpha %. So in this case, actually, yeah, okay. They gave alpha %. So alpha is usually like 5% kind of thing, right? So alpha is a whole number. That's why you want to, and you always compare with the 0.05, which is really just 5 over 100, which means that you should change the 5 here into an alpha. So alpha over 100. That's okay. Yes. And % means divide by 100 anyways. Then from there, you can solve for A by multiplying by 100. So you end up with the 6.18 GSF, but you want a set of values. Right? Set of values means you need to have set notation. You want a set notation, then you want the variable that is inside the set. The thing element inside the set. And it has to be an element of something. This is what we call the universal set. Here you choose R means set of all real numbers. If you choose Z, what does it mean? X an element of Z means X must be what kind of numbers? Z is? If the R got replaced with Z, what does it mean?
What?
No, you don't know
Integer?
this. Integer, yes, correct. So if this was Z, it would be element of integer, but we don't want that, right? We want our alpha to be real numbers, so we put down R. Okay, then you put dot dot is read as such that what? We must let the X follow obey a certain rule. Okay, in this case, if I never use X, I use A straight away. It must obey more than 6.18. This is the rule. Okay, this is how you construct a set. Give me the name of the thing in the set. It's an element of a universe. What universe? Usually all real numbers. If you change to Z, then you're telling us it must be integers. If you change to Q, it means it must be rational numbers. If you change to C, it means it's complex numbers. Whatever lah, huh? Then such that, you must follow the rule. And that's how you get the set. Okay?
Yeah.
Can all right. And
So
actually,
if they ask for set, I must do it like that.
right, in this notation. Yes,
Okay.
correct. Actually, this is not A lah, it's alpha. Okay, so you should write alpha like that with an extra tail here. Okay? Alpha. Okay. Okay, how about question 8? What happened? Mass-produced washers have thickness which are normally distributed with mean 3 mm and standard deviation 0.2 mm. So, very nice. It's normally distributed, so we don't need to use CLT. During a check on the manufacturing process, a random sample of 25 washers is taken from the production, and the mean thickness x bar mm is calculated. Find the interval in which the value of x bar must lie in order that the hypothesis that the production mean thickness is 3 mm will not be rejected in favor of the hypothesis that the mean thickness is not 3 mm at the 5% level of significance. Sorry. So you don't want to reject it in favor of the hypothesis that the blah 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 is not 3 mm. I think they're just telling you the alternative hypothesis, right? Good. Then will not be rejected. So you don't want to reject it means what happens? In order to not reject it, you need your p-value versus your 100 alpha %. What's the relationship? The inequality. To not reject, what do you need?
It's more than the level of significance.
Yeah, level of significance. Okay, good. So now, okay, can. Then let's see your working out. What do you have? You have under H naught x bar will follow normal, mean is 3, good. Then variance is what? Sigma square. Then you divide by n, 25. Okay, can. Then using z-test, you got a p-value 0.99999. Okay. Let me think a bit. So what do we want? Actually, here it's a two-tail test. Did you select the right option? Two-tail?
I also put two-tail.
Okay, let me check.
But when I key in, my p-value is set.
Wait. What do you key in for your mu naught?
Let me try again.
Can key in?
The mu naught is 3.
Okay. Oh, right. Mu naught. Oh, mu naught can. Then what's your x bar? What's your x bar? What do you key in for your x bar? Sigma is square root of the 0.2 square, which is just 0.2.
Oh.
Then what's your x bar?
Cannot key in because it's unknown.
Exactly, it's unknown. That was the point of the question. Okay, you cannot key in, so I don't know what you key in.
I think I key in the same 3.
Cannot. It has to be a sample that is given. In this case, they did not give you the sample. It's an X bar. Finally, we are coming to a case where using the GC just doesn't work anymore. Or syntax. Yeah, you must key in some number. Let's just pretend it's 1 or something. Then of course the n you can still key in 25, but the problem is with the, and also we must change the two-tail test. The problem is with the X bar. Okay, we don't know what value it can be. So we need actually a range of values that this could be. I'll just put dot here. We don't know what those values are. We need to find the interval of X bar such that we can not reject the H naught. Okay, so keep this in mind, and the X bar is unknown. Now we can just do it manually. So because the X bar is unknown, we cannot calculate the p-value directly. We now need to use the first method, which involves rejecting, checking that it is outside of the critical region. So we fail to reject H naught. How do we do that? First, you must always have your after your X bar, you need to have your
test statistic,
which is z following X bar minus way mu naught, in this case 3, divided by square root of 0.2 square over 25. Follows n, what is it?
0, 1.
0, 1. Very good. So now we need to calculate the test statistic instead. So let's just draw a graph again. What's the center line of symmetry? It's
0.
X equal to 0. Very good. So that means that we need what tail? This is a what tail test? Two tail test. So we need to cut 2 times. Cut here, cut there. Area here, area there. This is some z. This is some negative z. This is the test statistic. Okay. Then yeah, if you key in the GC, you may be able to get it. But here we don't have X bar, right? They are not given, so we cannot calculate test statistic. Then how? Then we have to think a bit more carefully. We want to reject it at the how many percent level? 5% level, right? Okay, so where is 5%? How do you represent 5% now?
It's both of the, like the tails.
Both of the tails, right? So that means that we actually need to cut off at okay, let me just move this X equals 0 away first. We need to cut off somewhere here, cut off somewhere there. And that's what we call the critical value, z crit and negative z crit. There will be a certain area. Let's just color in orange and orange here. What do we know about the sum of the two areas here? They must add up to?
The 0.05.
Very good. Which means by symmetry, each of them is actually 0.025. Can okay?
Yeah.
Then that means that we are able to form okay, what do you want to do actually? We want to make sure p-value more than this one, but in terms of the test statistic and critical value, what do we actually want? We need the z equals to something, some inequality versus critical value. What's the inequality here?
It must be less than
two-tail test. You have to be a bit more careful now. For two-tail test, let's just say that we need to, there's two possibilities, right? If you want to reject it, you must be outside the, sorry, if you want to fail to reject it, you have to be outside of the critical region, which means that your negative z here should be here, right?
Yes. So
yes,
it's
correct.
like
And the other guy,
modulus.
you need to be there. Correct. Yes. So it means that you need your modulus z for two-tail to be more than the critical, to be less than the critical value. And let's say we also take the positive, right? There's like a negative and a positive critical. Then the z also has a negative and a positive. So you want to make sure the positive guy versus the positive guy. I think it's easier to work like that. This guy and this guy, you need the positive guy to be less than the positive guy. This test statistic here is less than the critical value here. Does that make sense?
What?
Okay. Wait. Normally, when you have a left tail test, you have this area here representing your p-value. Then you have this area here to represent your significance level. Right?
Yeah.
Then if your p-value is less than your significance level, let's just call this 100 alpha percent. My alpha is usually like 0.05. So 100 alpha percent is my version of 5%. If let's say that this is less than your 100 alpha percent, your significance level, you conclude that you reject H naught. Alternatively, if your p-value is more than 100 alpha percent, this means you don't reject H naught. Clear so far?
Yeah.
Good. But now we translate it into the diagram, and then we look at its critical region. So if we want to not reject H naught, which is the purpose of this question, where should our p-value be? Our p-value should be, your p-value should be bigger, right? So that means if you can see my vertical line here, I'm moving around.
Yeah.
You see, you should move it a bit more to the right, such that it ends up over here, so that the area will be bigger than the orange area. Blue is bigger than orange. Correct? Your p-value must be bigger than your significance level. Your blue area is bigger than your orange area. Is that okay?
Yeah. Okay.
For you to not reject. Okay? So, but now if you translate it into the critical value and test statistic, can you tell me where is my Z crit? Can you tell me where is my Z, the test statistic? Can you label on the graph? Hint for you, it should be along the x-axis, one of the values. Where is it? Where's my Z crit? Where's my Z test statistic?
Right here.
Is which one? This is the
Z crit.
Very good. Yes. And of course, this guy here must be
The Z value.
The Z value. Okay, good. Yes, you got it. So here is your Z crit. There is your Z, just the Z. That is for left tail test for rejection. Of course, for right tail test, similarly, right tail test, you just reflect it. Okay, it's just a reflection. So we do the exact same thing. Okay, let me draw it nicely. That blue color area is your p-value with a Z being over at this location here. This is your Z. Is that okay for right tail test?
Yeah.
Then where is your alpha if you want to do not reject? It must be somewhere here, right?
Do not reject. Yeah.
Okay, then where's your Z crit? Can you draw for me? Where's my Z crit?
Like for this side.
For the right tail test, where's my Z crit?
Right here.
Okay. I think you meant to like move it here, is it?
Where?
Here, along the edge of the orange line, right?
Oh, you mean here?
Okay, is it?
I never see anything.
Wait, what do you mean? Oh, no, I'm just moving my screen so that I make sure your the line that you draw is aligned along here, right?
A long way? No, yeah, like
Can you see
the
my
screen is
annotation?
not moving. No.
Why is it not moving? Okay, wait. Oh, what's going on? Is it moving now?
Yes.
Oh no. Okay. Okay, I'll just review the answer. You mean here, right?
Yeah.
Okay, can. Oh, why was the screen not moving? Okay, good. Z crit is over there. Good. So now that we have seen that, how do we get two-tailed tests? Combine together, lor? Correct or not? Combine together. Okay, maybe I try to make it look consistent. Wait. Okay, so now if you combine the powers together, what do you get? Let's take a look. So what we have, that was left tail on the left. That was right tail on the right. So now my question is, so now I think it should be obvious. How would a two-tail test look like for your Z and your Z crit? Combine. Lo. So let me just draw the picture. Your combined picture will be for a two-tail test. You will have a line here, a line here, negative Z and positive Z. That's your test statistic value. It has a certain area. All the way to the left, all the way to the right. And then you have a Z critical. Where would the Z critical be? Can you try drawing? We want to, we're trying to draw the case where we do not reject. So we have a negative Z critical and a positive Z critical. Maybe I'll just put absolute value along this. Exactly, correct. Yeah. So let's just fill it in there and there. And that's exactly what I was trying to talk about, okay? This picture, can you remember it? Can? Okay, good. So now we're gonna take that picture, and that's what I was talking about over here. Modulus Z is less than modulus of critical value. The Z crit. I'm talking about this situation. Can you understand now?
Yeah.
For us to not reject.
Can.
Okay. Good. So now we can translate it back to the back to the question. So what do we need to do in order to get our Z value? Actually, this is our Z value already in terms of the unknown X bar. Then what do we need for about this Z value? This formula here, right? We need to satisfy this formula here. Can we calculate the critical value of modulus? At how many percent level again?
5%.
This is 5%. So we can actually calculate the Z critical, but we need to divide by 2, right? So
yeah,
let's just do that. Let me show you. Can I show both screens? Let me see. This guy. Share screen. This guy. And then. Do you need to rush off already?
Not yet.
Okay, can. Let me test first. Screen not showing, that's not good. Okay, screen is moving, good. And calculator. Yes, what was I saying? Now I want to calculate the critical value. So how do I do that? Go quick first. You go to second distribution. Go to inverse norm. Right, it's just inverse norm to get the x-axis value, x coordinate, the z value. You just have to take the inverse norm of what area in this case? It is 0.025. Okay. Which tail do you like? Of course it must be 0 and 1, right? Because it's z01. Z following normal distribution mean 0. Standard deviation is 1. Square root of the variance. So which tail would you like? Left tail or right tail?
Left.
Left tail will give you the negative value. Then right tail will give you positive. But of course, by symmetry, you know they're the same. Okay, negative 1.95996. So let's just translate it back into our diagram now. That just means that this fella here is our, okay, I use pink color, be consistent, our negative 1.95996. So of course, this other guy on the right side must be the positive version. Can I just remove this test statistic? I think you know, right? The Z without the subscript is a test statistic.
Yeah.
This is the positive guy. All right, good. So we can now form our inequality. We need this, which is our Z here, over here. It has to be less than this guy, right?
Yeah.
Of course, you can also take the modulus, but actually, since we are just trying to solve for an inequality involving x bar, I think we can play with we can play around with this and realize that all we need is actually just the Z value to be less than the Z critical. Oh.
Yeah.
So what does it mean? It means we can set up our inequality. No? This guy is the Z. Okay, wow, it's getting very messy. Let me get rid of this first. I'll move it down. I won't delete it. You can refer to it later. This one, and combine. Yeah. So what we need now, oh, I removed it. Where's my denominator? Is it this guy? What was the denominator? 25, is it? Sample size 25. So now, yeah, correct. Then we can just take this inequality and then we need it to be less than Z crit. Right, over here, maybe I draw a circle like this. This translates into Z is less than Z crit, which translates to our Z here, the formula for the test statistic, less than the Z critical value, which we have calculated to be by symmetry positive 1.95996. Then from there, you solve for x bar. Right?
Yeah.
But wait. If you look at a solution, the inequality has two directions. Do you see that?
Yeah.
Because your Z value could actually be not just less than that. It could also be more than the negative 1.9566. So that just means that you need a lower bound as well, negative 1.95996. Is this okay? That's the second half. Your Z can be anywhere in between here.
Yeah, can.
Which will lead to, oh, I never update my picture. The area is here and the area is there. This is the picture we have for rejecting H0. Sorry. For not rejecting H0. Oh my goodness. Okay, not rejecting H0. You need a Z to be in between here.
Yeah.
And from there, you can solve for x bar. Is that okay? Do I need to show?
Don't need.
Don't need, huh? Yeah, then you just solve for x bar and you'll get your answer. Okay, let's go to the next question. Wow, it's so long. What time do you need to go off?
Like 1 plus.
1 plus. Okay, let me see first. Okay, average discharge time of a new rechargeable battery is 13 hours. Alternative manufacturing process is 12. Discharge time P hours of each of 50 randomly chosen new batteries. Using alternative process is then recorded. New data is found. Results are summarized as the following things. Production manager wishes to test whether the average discharge time is different using the alternative process by carrying out a hypothesis test. Explain whether the production manager should use one tail test or two tail tests. In this case, discharge time is 13 hours. It just means your lifespan of the battery, is it? Yes?
Yeah.
So would you want better discharge time or would you want higher or lower discharge time? The lifespan. Higher, right? So that means should you do one tail test or two tail tests? There's one favorable direction. The manager is the this alternative process, you can think of it as like a young and budding scientist. A scientist come up with a new way. Then this manager is the one who is the enemy against the scientist. he doesn't accept the new thing. The scientist claims that he has a process that will alternative manufacturing process, right? I think you wouldn't want to trial a new test that is worse than the original, right? So that means that your H naught, you would want the T hours. Okay, I'll just call it mu for the mean time. Originally it was 13. You would want to come up with something that is lower, right? So the objective of the scientist is to come up with a new process that can produce batteries that take that can last for more than 13. So the manager is the enemy. So he goes against the more than 13. So what do you think is your H1 now?
But they just say it's different, so it can be different whether like better or worse.
Oh, okay, that's also true. Oh, right, the solution actually use a two-tailed test. Oh, that's why so a bit confusing. In this case, they just mentioned different, so you should just use a two-tailed test. Right, actually that makes more sense. Okay, sorry. Maybe I'm thinking a bit too much. This scientist is not actually there.
Yeah.
It's just different, so it should be not equal to 13. Two-tailed test. Okay, yes, you're correct. Sorry. This is right. Should be a two-tailed test.
My answer is like correct. Other than like the last part, I don't know what they're trying to ask me.
Okay, Ken. Let me just go to the last part then. Let's see. Marketing. Okay, let me read the question first. Test whether average is different. Two-tailed, one-tailed. Without knowing anything about distribution, yes, CLT unbiased estimate. Suggest reason why might be prepared to use an alternative process gives shorter average discharge time than the original process. Oh, what's your reason for part 4? Or maybe a better quality. Oh, okay, can. Marketing manager wishes to test whether the average discharge time is longer using the alternative process. The marketing manager finds the average discharge time of 40 randomly chosen new batteries using alternative process is 13.2 hours. He carries out a hypothesis test at the 10% level of significance. Part 5, explain with justification how the population variance of the discharge times will affect the conclusion made by the marketing manager. Okay. In this case, if you change your sigma, then you may change your conclusion about whether you reject H naught or not. So the answer they gave was what? If you manage to get this guy to be less than 0.987, you will end up having to change your conclusion. You will have to end up saying that the average discharge time is longer. So you fail to reject H naught. Okay, so let's just figure out what's your H naught and H1 first. Let's see what you wrote down. So H naught means discharge time is 13. H1 is this one is the actual one. He wants to show that the discharge time is more than it's longer using the alternative process. So that's why it's a more than. Then under H naught, you get this guy over sigma square over 40. This is unknown, so you keep it at sigma. Okay. Can. Then you use CLT because they never tell us what's the distribution of X itself. So Z follows N01 now, but of course the Z is just X bar minus away mu naught divided by the square root of sigma square over 40. You should write down the formula as well. So that in case we need to use the test statistic formula, and which in this case we do and you wrote down over here, is it? Yes, correct. Just use this, but you substitute the X bar with the 13.2 value. Is it 13.2? Yes, they told you the sample of 40 has the average discharge time being 13.2 hours. So you substitute 13.2. Now, in order for you to do what? What are you doing here? You try to reject H naught. Okay, so maybe you need to make an assumption. to follow the sign of H1. Oh yeah, you should also mention here to reject H naught. Okay. Do you get what's going on?
Yeah.
Here we cannot compare with everything else. This is if this sigma was known, right? We would be able to calculate our actual test statistic value. Then we can compare with our critical value here. You took inverse norm, right, to find this 1.2815.
Yeah.
Yes, or then we will be able to directly conclude whether it's less than, equal, or more than. Here you purposely chose a more than. It means that you are assuming that you have rejected H naught. Okay, and that's fine. That's fine because we're just exploring. We don't know what is sigma yet, so we just say that it's more than. We assume we can reject H naught. Then we see where that leads us to, and we realize that we need the z value to be more than the critical value, so that it's if you draw the graph, here's x equal to 0. Oh, the graph not so nice. Let me try again. We need our critical value z crit to be somewhere here, and our maybe I'll move it a bit more to the left, and then we need our test statistic here to be a bit more to the right, such that the area over here, the p value is less than the alpha. That's how we reject. What you said here, follow the sign. Okay, can also. More extreme, huh? Yeah, or inside the critical region. The test statistic is inside the critical region. Now, more than, then after that you can solve for sigma. What did you get? You got this answer. Okay, fine. So that is the value of sigma such that we will have this conclusion, reject H naught. Do you agree? They go in both directions.
Yeah.
So the question is just a very simple one. You just have to say, if it wasn't this value, then you have to end up not rejecting H naught. Not reject H naught means what? Means you have sufficient evidence to conclude that H1 is true, meaning discharge time is more than 30. Yeah, just use the standard phrasing. Not much to it. Just say when just describe something related to the sigma. If it's less than, you reject H naught. If it is more than, then you accept H naught. Except if it's the other direction, more than equal. Okay.
Then what is the last part asking for?
Huh? What last part? Explain with justification how the population variance of the discharge time will affect the conclusion. What I said lah. The conclusion is reject H naught or accept H naught. If it is less, reject H naught. If it is more, then you accept H naught.
So that's how to phrase the answer.
I guess so. Yes.
Okay.
But of course, you must contextualize. Don't just say reject H naught. So reject H naught will mean discharge time is not 13. Or you can also say the standard phrasing, which is, what's the standard phrasing? When you make a conclusion, this guy, just use one of these and write down something. Given the condition that the sigma is less than something, 0.987.
Oh, okay.
Okay.
Can.
And yeah, just give a comment. What is the next question? Oh, let me see. Okay. Question 10. Okay. Sorry, I need to use the toilet. Can we have a short 5-minute break?
Yeah, sure.
Okay, I will be back. Mic test.
Yeah, can hear.
Okay. Can. All right, where were we? Oh, you have a question here? Does not lie in critical region H not rejected. Does not lie in critical region and H naught is not rejected. Yeah, okay, can. You can say that as well.
Okay.
Just say something logical lah. This one. Just make a comment. They are trying to test you whether you can understand the idea of rejecting H naught or accept H naught. Inside the critical region, reject. Outside, then do not reject. That's essentially it. Okay.
But why the answer talk about like population variance?
Population variance.
That's related to Z value.
No. That's just the sigma. That's just the English word for sigma. Right? They gave us sigma. We didn't have to calculate the
But I thought it's sigma square.
Oh, sorry, sigma square. Yes, sorry. Yeah, correct. Standard deviation is sigma. Sigma square is the population variance. That's why they have 0.987 square. Sorry, my mistake. Yes. Why are they're just saying sigma square? You can always talk about sigma. I have no idea why they wanted to talk about variance. They could have mentioned standard deviation. It's perfectly fine.
Okay.
Yeah, it's the same. Don't worry. I guess that is all. Okay, moving on. Now, question 10. Let's see. So our consumer association is testing the lifetime of a particular type of battery, claimed to have a lifetime of 150 hours. Random sample of 70 batteries is tested. Lifetime is summarized like this. The data is summarized in those two. Population mean lifetime is denoted by mu hours. Null hypothesis is mu equal 150. Tested against alternative hypothesis mu less than 150. Find the p-value of the test. State the meaning of this p-value in the context of the question. The meaning of p-value I mentioned at the beginning of the lesson. Cut. Now you got second random sample of 50 batteries. This type is tested. Lifetime y hours of each battery is tested. Summarize again. So of course you have to recalculate your unbiased estimate of the mean and variance. Then combining the two samples into one single sample, carry out a test at a 10% significance level of the same null and alternative hypothesis. So combining the two samples, that sounds very familiar. Sounds like something we did last lesson in the sampling. We'll deal with it later. Let's focus on the first one. What happened? Let me read your solution first. Mu equal 150, mu less than 150. How did you get 150? Because of their claim. Okay, fine. Then the x bar, you just have to take this divided by 70. Then the s square, I assume you calculated it correctly. Yeah, this is fine. Okay, the working is fine. Then after that, using the z-test, you calculate the p-value. Seem to skip a lot of steps. What happened to my CLT? What happened to my test statistic?
I didn't write the test statistics since the start because I didn't know need to write.
Okay, right. Then but at least need to write down the CLT lah. You must say that x bar follows a normal distribution. In this case, the mu you have to use the unbiased estimate. Oh no, wrong. No. You should be using the h naught value, mu naught. Then you divide by the unbiased estimate of the variance s square divided by n. In this case, it's 70. This one you have to say it's approximately by CLT. Then for the next branch, you need to mention the test statistic. Z equals to x bar minus, in this case, the mu is 150 divided by the square root of sigma square over n. So it's just 284.82. Divided by 70. And this follows a N01. Sorry for squeezing. I should be writing this all in one line.
Oh,
Yeah.
okay.
I hope you understand what's going on.
Yeah.
Okay, good. So yeah, then you can use the z-test to get the p-value. That's fine. Then next, second half, second random sample. Oh, what is this? No, sorry. Still need to find the p-value and state the meaning of this p-value. Okay, so let's see. Where did they get? Let's read those correction you did. The p-value is the probability that the mean battery lifetime of a sample is less than 147.39 when the actual population mean battery life is 150. So let's recall again what is the definition of p-value, and the template we have over where? Over here. Okay, probability of obtaining an inequality or inequalities involving the test statistic, which is more extreme than the mu. Now, let's see. Yeah, so in this case, right, okay, hold on a second. Let me see. Okay, here they're just using, yeah, I think it is the same format, right? Is it not? Let me show you the whole screen. Can you see the entire screen?
Can.
Can, okay, good. So let me try and make it a bit bigger. Is this better? Okay.
Yeah.
Make the screen a bit smaller. I don't know. Need to adjust. Okay, and go here. Yeah. I think it's a bit better. So here, let's just look at the template. Okay, it's over on the right side. So let's just see. Does it follow the template? Let's see. Probability that the mean battery life of a sample is less than 147.39. What does that mean? That's actually the number one in my template. Inequality or inequalities involving the test statistic, which is more extreme. So that's actually 1 and 2 combined together. Here the 147.39, if I'm not wrong, that's your sample. That's your sample, right?
Yeah.
Let me think a little bit. Actually, that phrasing is a bit funny. They didn't mention. When the actual population mean is 150. That phrasing is a bit funny. Let's see. Actually, I am a bit confused by their phrasing. Let me see. doesn't really make sense. Sorry, give me a moment to think about this. What is a p-value? Okay, let me read out the definition of p-value for you. Okay, a p-value. Okay, I'll write it down for you. I'll write it down.
Oh, okay.
Yeah, I don't need to stress too much about this. P-value definition, it is the probability of observing a test statistic I don't need a dash. As extreme as or more extreme than the obtained value, given that H naught is true. As extreme as the obtained value, or more extreme than the obtained value, given that H naught is true. So using that, okay, I think it makes sense. I think it makes sense for their interpretation. So what that means is that the value that is obtained, right, is actually the decimal ones. So you are asking, where did they get this 147.39, right?
Yeah.
Okay, why is my highlighter not working? Hold on a second. Eh. Sorry, wait a minute. Highlighter working again. Okay, good. Let me share screen. Yeah. So what was I saying? Yes, this 147.39 is actually the value that was calculated from the sample mean, right? So that is the value that is obtained. Okay, the obtained value. Right. Then we want to. It's the probability of observing a test statistic, in this case, the mean battery lifetime of the sample. And you want it to be more as extreme as or more extreme than the obtained value. And this is the obtained value we obtain from our data. Right? And it has to be more extreme or less extreme, or more extreme or as extreme. In this case, it's basically telling you the rejection region. So in this case, it must be less than in order for you to be more extreme, because we are doing left tail test. Right?
Yeah.
Does it make sense? I hope it makes sense.
Yeah.
Or of course, in general, you can think of it as the area law. The area obtained from that z value, and then you travel in the same direction as the alternative hypothesis. So you have your z, then you got the area. If this is a left tail test. So that is also p-value. This guy here. Okay. This they got it from here, the obtained value. Okay, Ken. Next, what is it? Say the meaning done. Then you have a second random sample. 50 batteries of this type tested, and the lifetime Y hours of each battery is measured. Results are summarized as below. Combining the two samples into a single sample, carry out the test at 10% significance level. Same null hypothesis, same alternative hypothesis. So 150 and 150 equals and less than. So let's see. They gave an alternate. Okay. What is this? Okay, I'm going to ignore this second interpretation of p-value. Ken, let's move on.
Okay.
All right, then what do? You combine the two samples, right? So you should introduce a new random variable t. That's okay. Then what did you write here? H equals to 70 plus 50. Oh, I think you meant the new sample size, is it?
Yeah.
I think it's okay to just recycle the n. For this case, it's clear enough. Oh, there won't be a confusion. N equals to the new sample size 120. Then here you want to take the summation. So it will just be sum of x plus sum of y. Right? Okay, fine. Then after that, you want to take the sum of y, sum of the t square. It will just be sum of x square plus sum of y square, which will be this guy. You add them together. Actually, hold on a second. It's a bit off. This is like 1 million. This one is, sorry, 1.5 million. This one 1.1 million. Here, you only got 264,000. Wait, what? Do you see the problem? I think you missed a zero or something. This should be not 6, but 96. 2,640,796. Yeah, I think you key in wrongly or something. Right? Okay, okay.
Yeah.
Good. Then therefore we can now calculate our T bar. Hold on. Wait. T bar. Can. Yes, you just need to get the divide by the n. You just need to take your sum of t, then you divide by divide by the sample size, and then you get your t bar. And then you need your s square, right? But you found s straight away. Okay, that would be what? That would be the formula 1 over n minus 1 multiplied by sum x square minus way sum x bracket square over n. Now you can just fill in the blank. Instead of x, it should be a t. So sum x square, we already calculated it over here. I don't know if there's error carried forward. Maybe you just forgot to write a 9. That's why you could still get the final correct answer. Let me double confirm. Actually, just look at the solution key first. Answer key. Okay, got 147, which is fine. Then how about S? You got 381. Okay, it's fine as well. Okay, can, good. Then in that case, your new H0 and H1 is actually just the same as the old one. But of course, it's for a different scenario. What happened in this scenario? A second random sample of 50 batteries. You got new data. But no, we are trying to combine them, and then we carry out the same test, same hypothesis, same null, same alternate hypothesis, and then we do the 10% significance level. Previously, it was how many percent? Oh, previously we didn't do a hypothesis test. We just calculate p-value only, and then we stop there. Here we are doing a z-test to get a p-value, and then you compare with 10%. You realize it's less than that. So because this is a left tail test, and you have less than, it means that you have to reject at 10% level. Sufficient evidence to show that the alternative hypothesis, here is true. It's less than. Okay. Ken. No questions,
No.
Okay, question 11. Let's see. Now they make a n unknown. Let's take a look. So bags of salted cashew nuts, they display net content 100 grams. Manufacturer knows that the standard deviation of the population is 1.6 grams. Customer claimed that the bags have been lighter in recent purchases, so the factory quality control manager decided to investigate. He sampled N bags and found that the mean weight was 99.4 grams. He sampled a 1% significance test and concluded that the customer's claim was not valid. So he managed to do a hypothesis test and show that the customer is not true, is not making a valid claim. So H naught is mu equals to 100. Then H1 is the alternative hypothesis. You want to argue that it's less than the claimed 100 grams. Okay, can. So the manager is pretending for a moment that he is the customer. So he goes against the factory. He goes against the factory. That's why it's less than 100. Yeah, okay. Then you let X be the mass of a bag of cashew nuts out of N bags. Okay, can. Then X bar will follow this distribution, 100 here, not 99.4, comma, sigma square over N. In this case, what is sigma? It is just 1.6, so you just take 1.6 square over N. Can. You are assuming that N is sufficiently large. And also, this is by CLT. Yeah. I think this one is very important, must mention, by CLT. Okay, otherwise you can't get a normal at all. Okay, must mention by CLT. Then central limit theorem. Then Z will follow normal distribution. Maybe you should include a test statistic statement. So Z is equal to X bar minus Y mu naught. In this case, the mu naught is 100. Then you divide by the square root of the 1.6 square over N. Follow N01. Then let's just carry on. A customer claimed that the bags have been sampled N bags, found that the mean weight is 99.4. That's your X bar. Then he performed a 1% significance test. Okay, so you took a critical value, you got negative 2.3263. I think you are taking 1% in your inverse norm, right?
Yeah.
Okay, let's just calculate that. So second distribution, inverse norm, the area in this case is 1%, so 0.01. Then you have mu zero sigma is 1. Then you want to do a left tail test. So we can get because our left tail test, because the H1 here is left tail. So paste it and you obtain negative 2.326. Okay, good. Yes. Then the Z value, you need it to be less than the critical value in order to reject H naught. Same direction as the alternative hypothesis. Yep. So inside the critical region, so you can reject H naught. Okay, good. But hold on. That's not correct. Actually, I just realized you don't want it to be rejected. Because if you reject H naught, what happens? You end up with H1, which is mu is less than 100, which means that the customer's claim was valid. Do you get what I'm saying? He conclude customer's claim is not valid, means that H1 is false, which means that H naught is true, which means that we do not reject H naught. Is that clear? Mic test, can hear? Hello?
Yeah, so I put more than the critical.
Oh, okay, right. Okay. Oh, you write down this one, the other direction. Okay, not to be rejected. Yes, correct. Okay, can. Then after that, you just take the test statistic, but you substitute the X bar with the value, which is 99.4 from here. Then you try to solve for N. And then you're able to obtain. Okay, this is correct. Can. No questions, huh?
No.
Okay. Can. Let's see. Question 12. What happened? An alpaca breeder wants to produce fleece which is extremely fine. In 2008, his herd had mean fineness of 22.3 microns with standard deviation sigma microns. The standard deviation remains relatively constant over time. In 2012, a sample of 80 alpacas from the herd was randomly selected. The mean fineness was 21.2 microns. Find the range of values of the standard deviation, which will indicate a significant change in mean fineness at the 5% two-tailed significance test. Okay, can. So here the alpha is unknown. So wait a minute. Not the alpha, sorry. The standard deviation is the one that is unknown, a sigma, and we need to find a range. So let's just look at the H0 and H1. You got H0 is 22.3, the mean finals. And then you have H1. You want to do a two-tail test such that it is not 22.3. Then you what? You let the actual mean fitness of fleas in 2012 be the random variable x and the standard deviation be sigma. Okay, can. Then this guy, you get x bar to follow normal distribution. The mean here should be the mean from 2012, 21.2. Then it will be sigma square over n, in this case 80. Here you need to mention approximately by CLT. Because they didn't mention that it's normal distribution. So you can only conclude it's normal because of CLT. Then you should also mention the test statistic. Okay, I'll leave that to you. And 0, 1. Then after that, Z critical value, you just have to take the 5% significance level and you inverse norm. But here, answer key tested 1% level of significance. I think that was what you were asking. Let me just take a look. What did they do? Oh, you're right. The answer key is wrong. Can't be 1%. Has to be, you have to follow this guy. 5%. Okay. So the answer key is wrong. Okay, that's problematic. Let me see. What percent do you use? What percent do you use? Do you follow the question? 5%?
I use 5%.
Okay, then we'll ignore the solution. I'll do it live. Let's do the 5% one. So in this case, if it is 5% two-tail test, right? It means that it's actually 2.5%, 2.5% on each side. Right? So here the area is 2.5%. There will also be 2.5%. Total will give you 5%. Then what we want to find is this value here, the Z crit. So let's just calculate that. So area in this case is 2.5 divided by 100. So 0.0, let me think, 0.025, yeah. Then mu and sigma must be 0 and 1 because we are looking at a standard normal distribution. This is a left tail. I like to calculate left tail. It's my convention. Okay, then you end up with a negative 1.599. 9599. This is your Z critical. The negative version. The negative version. Okay, then in this case, you. How did you get this guy? 0.06. That's not very accurate. Let me think. Did you key in a 0.505% instead? I changed the. I just jumped there. I just edit directly. I hope you understand what does this mean? Inverse norm.
Yeah.
Cannot. Is this what you did? Also not correct. How come got negative 0.06? That's a bit weird. That's not very accurate. Yeah, I don't think it should be this guy. Okay. Yeah. So what you need to know is that whenever you do two-tail test, they give you this alpha percent, right? Alpha has to be split into 2. So alpha over 2%, alpha over 2%. Okay. Then when you do Z critical, you want to find that critical value. You take the inverse norm. Just pretend that this is like a left tail test already. Then you just take the inverse norm in order to find this critical value. Is that okay?
Yeah.
Negative 1.95. Okay. So now we can carry on with the negative 1.9599. What do we want? We want to make sure that we have a significant change in mean fineness, which means we reject H0, accept H1. Sufficient evidence to accept H1. So if you want to reject H naught, what do you need to do? You need to make sure that you have a, what is it? You need to have an inequality like this. Your critical region is now here, and you must stay inside the critical region. So that just means that your Z value must be less than those critical values. Or the other case will be Z is more than the positive. Is that clear? Oh.
Yeah.
Can, right? Okay, good. But of course, that's in terms of inequality, that will be the modulus is less than the positive 1.95. But yeah, so yes, you got it. It's just that the value here is not that, it should be a negative or positive, sorry, 1.9599. Let me see if you calculated this correctly. Basically, you take the Z, the X bar minus away the mu naught from the H naught, and then you divide by the sigma square over 80 variance. Good. Simplify this, square root sigma square root 80, you can multiply square root 80 on top by this negative 1.1. Then you will end up with, oh, you flip it around. So you flip around on both sides of the inequality, then you change the direction of inequality. That's correct. Good. Oh no. This guy should be 1.9599 on the denominator. Then 1 over that, and now you can just modulus top and bottom. This guy become positive times over. Then you get modulus of sigma to be something. Let me just solve it quickly. So modulus of sigma will be less than 1 over 1.9599 multiplied by modulus of square root 80 times negative 1.11. Negative 1.1. Okay?
Yeah.
Then after that, you can just solve for sigma. Let's just calculate it here. Square root 80 times 1.1. You can just throw away the minus because it's positive. Then you multiply by 1 over 1.9599. This will give you 5.0 equals 5.0200. Then modulus is less than 5.02, so it means negative 5.02 is less than sigma is less than positive 5.02. That's your final answer. Is that okay?
Yeah.
Can? Okay. Then supplementary. Oh my goodness, I don't have time already. Shall we continue this on another lesson? Hypothesis test.
Can.
Can. Okay. May I know? Okay, wait, let me just pause the video. Stop.